Hi friends, this video series is going to be a complete course on Sagemaker. Sagemaker is a machine learning platform from Amazon AWS. In this series of videos, we are going to cover end-to-end machine learning lifecycle from data gathering, data cleaning, data engineering, the training the machine learning models and deploying the models in different modes as endpoints, batch inference, and within endpoints, we will see the serverless endpoints as well as multi-model endpoints, right? And then we will see the pipelines where we stitch together a number of steps from data engineering to training the models to post processing the results, etc. We are going to cover the full life cycle of ML ops and a number of SageMaker products such as Clarify, which help us understand and interpret the ML models, and also Lineage, which will track the machine learning process, the various steps we take to build the models, right? And this course is not only restricted to the SageMaker. We are going to learn the machine learning use cases in general. For example, text processing, image processing, the computer vision, object detection models, image classification models, etc. And we are also going to see the Jumpstart models from SageMaker. So SageMaker has took the libraries such as TensorFlow, PyTorch, Hugging Face, etc. and made them easy for us to use in the form of these Jumpstart models. We are going to cover those Jumpstart models as well as we will cover the transfer learning as well. Now, SageMaker is a very evolving product. AWS keep adding new features to it on a regular basis. So as those new features get added, we will cover those features also. Now we can access SageMaker in three different ways. The first one is from our local environments like Jupyter notebooks, VS Code, etc. So for that, we need to have AWS access key and the secret. So what you can do is you go to the terminal and just type AWS configure. Okay, then that will ask you to enter these four details. So get your access key and secret access key from your AWS user account. Then the default region, whichever the region you are in, and then the default output format. This is generally the JSON. So in the description below, I provide this link where you can find more details about how to configure this AWS credentials. So in this course, I will be accessing the SageMaker, training the models, deploying them, etc. Everything from my local Jupyter notebook. Okay, so that's one way of doing. Now the second way is by going directly to the AWS console. So go to your AWS console. Here you can search for SageMaker. Search for your SageMaker. And then under the notebook, you see notebook instances. So here I have already created two instances, but you can create a new notebook instance. Give it a name. Now choose an instance type. Now this don't have to be a big instance because here the actual model training is going to run on different instances, much larger instances. This instance just act as a base so that we can give the instructions to the instance where we are actually training the models, right? So you don't have to choose a very big instance. Choose a moderate one like MLT3 medium. Okay, and then here you have to give an IAM role which has the permissions to execute the SageMaker. Okay, and you can leave these three as optional. Simply click on create notebook instance. So that will create a notebook instance like these. So here I have two instances. One is MLT2 large and MLT2 medium. And once you have created this instance, you can just choose the instance and click on start. It will take sometimes a couple of minutes. So once the instance start, here you will see open Jupyter Notebook. So you just click on that, and then you will have your Jupyter Notebook just like you have in your local environment, right? And whether we run any code or not, we will get charged as long as this instance is in running mode, right? So it is important that you stop the instance once your work is done. So for example, let's say this instance is running and you want to turn it off. So again, choose the instance. This under actions, you will see stop, right? Because it is grayed out because this instance is not in running mode, right? So don't forget to stop the instance. Don't delete the instance because that will delete all your data. Okay. All right, so that's the second mode, the notebook instance. So it's exactly similar to how we use notebooks in our local environment, except that this notebook is also running on one of the Sagemaker EC2 instances. And the third mode is the studio. So you click here. Now again, I have studio profile, so that's why it is saying this studio, but it will show you if you are doing it the first time, it will give you options to create the studio. Again, very straightforward setup. It will take you a couple of minutes to do the setup. And once you have done it, you can open a Jupyter Notebook from the Sagemaker Studio as well. Now, the notebook instance, it does not have any additional features, whereas Studio has a number of additional features. Like we can see it is a complete IDE environment. We can see the pipelines, the MLOps lifecycle related functionality, etc. So we will see those functionality as well. We will be interacting with those pipelines, etc. When we get there, right? So for the time being, simple Jupyter notebooks are enough to start learning AWS SageMaker. Okay. Yeah, so as I said, this is going to be a very long course, and AWS keep adding new features to it, and we will be covering a lot of aspects, the new features, etc. as they get added to SageMaker. Thank you very much. See you in the next lecture. Bye. Today we will prepare the data to train a classification model using XGBoost algorithm and a SageMaker. Okay, so here we are importing a bunch of libraries, the pandas for working with the data frames. We are going to access the data using sklearn library, and we are going to split the data into train and validation using train test split, and IPython display. This is for just displaying the images. Now we don't need the Boto3 and logging libraries for this data preparation, but without so the notebook, if you are going to execute any commands related to AWS, it's going to say the found credentials in this AWS config file, right? So it's an unnecessary message. So in logging level, it's called info. So with this, what we are trying to do is we are telling the notebook display only the information if it is at least warning level, right? So with these 3 lines of code, we are simply suppressing the info level messages, right? Other than that, we are not going to use these libraries. Okay, so the dataset we are going to work with, it's called Iris dataset. It's a flowers dataset. Now, as you can see here, there are 3 variations of this flower called Setosa, Versicolor, and Virginica. Okay, so these are the flowers. Now here we have this cartoonish representation where we can clearly see the differences. So they have, the flowers have what is known as these petals and sepals. They look different for each flower. Okay, now the petal has a length and width. Similarly, the sepal also has a length and width. Okay, so as you can see from this cartoonish image, the sepals are generally longer. So for example, this one and this one, these three, and also these three. So they have this this distinctive structure in the middle. Okay, so that's sepal, and then the petal, it's this one and this one and this one. Okay, so what we are going to do is we are going to have a data with 4 variables: petal length, petal width, sepal length, and sepal width. Now, given these 4 variables, we are going to predict or classify which type of flower it is. Okay. All right. So from the dataset from scikit-learn library, here we are accessing the iris dataset. Now the data type is the scikit-learn this bunch. So it comes with a, in addition to the data, it comes with a bunch of methods. So here you can see all the methods using this direct dir iris. Now it has this description. So first let's look at the description. Okay. So we are looking at the description. Now the number of records is 150. The number of records, I mean the number of flowers. So a scientist, he went to the field and he collected these 4 metrics from 150 different flowers on the field. Okay. Now, as we discussed, we have 3 classes. So of these 150 flowers, we have 50 flowers for each class. Okay. Again, the dataset has these 4 variables measured in centimeters, and then also has a class variable which is one of these 3 for each record. Okay, here we have some summary statistics, the maximum, the minimum of the sepal length, width, petal length and width, and we also have the mean and the standard deviations. Okay. All right, you can read more about it if you are interested, but that's pretty much about the data set. So now we are going to create the pandas data frame to prepare the data, right? So from iris data, it has these 4 feature values as we discussed. Okay, so here we are trying to create a pandas data frame with the iris data, and the column names are iris feature names. Okay, so at this point our data frame has these 4 columns with the values, and then we are adding the target variable called class using iris target. Okay, and here we are looking at the first 5 records of this data frame, and then iris has another method called target names. So here we have the 3 target names: setosa, versicolor and virginica. So in the class we have these numerics 0, 1 and 2, right? Whereas the target names are setosa, versicolor and virginica. So we can map 0 to setosa, 1 to versicolor and number 2 to virginica. That's because in machine learning model we work with only the numbers. So that's why these flower names are mapped to the numerics. Okay. So just looking at the data frame shape, so we have 150 records and 5 columns. 4 of them are features and 5th one is the target variable. Now here we are counting the distinct values for each class, right? So okay, so class 0 we have 50 records, class 1 50 records, and class 2 also 50 records. So it's a very balanced data set. Now we are going to train XGBoost model inbuilt into Sagemaker. Now this model expect the target variable in the first column. So we are going to do a bit of data preparation here. Okay. So data frame dot columns, this will return all the column names. So we will have the 4 features as well as the target variable name here, as you can see here. So we are printing the columns, these 5 columns. Now we want to reorganize these columns so that we have the class first and the remaining features next. Okay, so here we are accessing the last element of this list, that would be class. Okay, and then here we are accessing all the names except the last element. Those would be 4 features. Okay, we simply reorganize these columns. Now they would look like this. Okay, first class and then the remaining 4 features. So here we are just recreating the data frame using the original data frame, but we are simply reorganized the columns. So now the data frame looks like this. Okay, so all we did is we move the class column from the last to the beginning. Okay, that's all we did with this code. All right. Now, so we are going to train a machine learning model. So that means we are going to have some training data. We are going to keep some data for testing or validation, right? So we are going to split this data. Now we are using the test train split method from scikit-learn library. This is the data frame. And we are saying, I want to use 33% of the data for testing. So for training, the remaining 67% of the data. Now the random seed, it's an optional variable, but by giving this variable, we can split the data in the same way. So for example, the records which go to train and the records which go to test will be the same if we are using the same random seed, provided all other variables remain the same. Okay. Sorry for that message. All right. And then the stratify, this is very important. What it does is, as we saw, we have 50 records for each class. And we are saying we want about 2/3 of the data for training, 1/3 of the data for testing, right? So for each class, it split the data such that we have 2/3 of the data in the training and the remaining 1/3 in the testing. Now, this data set is balanced, so it might not be that important, but whenever we have this highly imbalanced data set like customer churn or fraud detection, etc., where we will have highly imbalanced data sets, right? For example, if we have 10,000 customers, probably 9,900 of them don't churn, only about 100 of the customers churn, right? So when we split the data, it is important that the rare class also split into train and test with the proportion we choose here, right? So if it is those 100 rare classes, when we do the split, about 66 of them goes to the train and 34 of them goes to the test. Otherwise, what will happen is among those 10,000, randomly 2/3 of the data goes to train. Now it might happen that all the 100 records or maybe 95 records might simply go to the train. So the test data set will have only 4 or 5 records from the rare class, right? So that's why it is important to stratify using the target variable, so that even those rare class records get distributed to train and test as per our split proportion here. Okay. So in this case, we have roughly 33 or 34 records from each class chosen for training, and the remaining 16 to 17 records for each class are chosen for validation. All right. And then we are writing the data to a file called iris_train. We don't need the index column. This is that by default, when we write data to a file using pandas, it creates an additional column with serial numbers 1 to n, right? We don't need that. And also we don't need headers. As we discussed, machine learning models, they only work with the numbers. So we don't need to give the column names to the ML model, right? And then we are creating the test dataset. We are writing the test dataset here. All right. And then we are going to do what is called batch transform, right? Where we give a number of, we apply the machine learning model on a number of records at the same time, right? So for that, we will have only the feature values, right? We don't have the target in the file, because that's what we are trying to predict. Whereas in these files, we need to have the target variable as well, so that from this file, the machine learning model try to learn from the features and try to map those features to the target variable. And with the test data as the model training, it apply its learning on the test data to see how good it is performing, right? After the model is trained, then we do the batch transform. So by that time, the model has already learned how to map the features to the target variable. Now we want to test the model. So we will input only the feature values, right, during the inference. Okay. So what we are doing is, from the test data, we are simply dropping the class column, and we have created a new data frame called inferdf. So this will have 4 feature variables. Now we are writing this to another file called iris_infer, right? All right. If you look at our file format, this is how it looks like. Just printing the head or the first, I guess, 10 records from the files. So the train data file will have the target variable in the first column. This will either be 0, 1, or 2, mapped to 3 different classes. And then we have 4 different features. Okay. And for the infer also, so the test will also have same structure. Whereas infer will not have the feature in the first column, sorry, target variable in the first column. So we have only the 4 feature values in the data file, right? And then now Sagemaker expects all the data for training, validation, etc. To be on S3 storage, right? So we prepare the data set locally. Now we are going to upload the data to S3. So we are uploading the train data to this S3 path. So I already have created a bucket called Sagemaker course. And then I have this prefix iris/data. So we have uploaded the file, the training data file. Similarly, we uploaded the test data file. And then the infer data file, we are uploading it to another folder called the batch transform. Okay, so this is how it looks like on the, I'll show you in a second how it looks like on the Sagemaker, S3 console. Okay, now we don't need this, but I just want to show you one interesting thing. So all we are doing is, we are simply doing the pair plotting between the 4 feature variables. Okay, 4 feature variables. And we have color coded the data so that we have different color for each of these classes, 0, 1, and 2. Okay. Now let's look at only this, the middle ones, right? Here we have the histogram distribution of the each feature value. Now the sepal length and sepal width, they sort of overlap. There is a significant overlap in the distribution for different classes. Okay. Whereas for the petal length and petal width, the distributions are, there is no overlap. I mean, there is some overlap, but there is quite good separation, right? So what this means is, using the petal length, we can easily distinguish these 3 flowers. Using also the petal width, we can distinguish these 3 flowers. And especially this class 0 is very, very distinctive. Now sepal width and sepal length, it's hard because their distribution is overlapping. All right. Let's look at this. Let's look at in the images if petal is a better predictor or sepal is a better predictor. Okay, so if you look at the petal, yes, it is different. So for this flower, it's of this size. For this flower, it's like this. For this one, it's quite big, right? Whereas the sepal for versicolor, setosa, and virginica, it looks very similar, right? For these three different flowers, sepal looks very similar. The petal is very distinctive. So petal should be a good predictor for distinguishing these flowers, which is what should we are seeing here. Okay, all right. Let's go to the Sagemaker console. AWS bucket S3. All right. So this is the bucket we have, Sagemaker course, and then we have Iris. We have a new folder for this project, and then in this data folder, we have the train data and test data, and then in batch transform folder, we have the infer data, right? So that's it. We have prepared the data, and in the next step, we will train a machine learning model using Sagemaker inbuilt algorithm, XGBoost. Thank you very much. In this video series, we are learning about AWS Sagemaker. Now, all the notebooks related to these videos are in the GitHub, the link provided in the description below. Okay, so in the previous video, we have looked at the data preparation to train a classification model, right? We have prepared the data and we have uploaded it to S3. Today, we will use the data to train inbuilt XGBoost model. Okay, all right. So in each video, we might be using some new libraries. So I will discuss only those new libraries. The previously discussed one will assume you are already familiar with it, right? Okay. So the date time, this is just to get the timestamp. So we are going to train a model. So for that's called training job. We want to give a unique stamp to the training job, and we might be creating some endpoints, etc. So for each, we want to give a unique name. So we will use the timestamp for that. Okay. So the AWS and SageMaker related specific libraries, the Boto3. This is a Python SDK for AWS. Not just a SageMaker, but we can interact with pretty much all the services of AWS using Boto3. And then we are importing the SageMaker. We are importing this training input for inputting the training data. Now, image URIs. So from this, so what SageMaker did is they have containerized the machine learning models. Okay, so they have created these separate Docker images for each model. So what we do is, for each model, we have a model ID or name, and using that, we retrieve the Docker container URI, right? That's we will use when training the model. And then using this function, we can get the hyperparameters for that model. Okay. So as we have seen in the previous video, this is just to suppress the information which is below warning level. Otherwise, we will see found credentials in this AWS config file for all the AWS commands, right? That's what we are doing. Okay. Then the region. Because we already know, we can either use the input the region as a string directly, or we can access from the SageMaker session also what region we are in. Okay, and this is important. So if we run this code directly on either SageMaker notebooks or SageMaker Studio, so using the SageMaker, we get execution role. We can directly get the execution role. Okay. But if you are running the notebooks from local, this command won't work, right? So get execution role command will not work. We will have to give we will have to explicitly give the Sagemaker role ARN. So this is a role I have created in my AWS account, which has the permissions to run the Sagemaker modules. Okay, so I got the role ARN and I have put it in my environmental variables. So from the environmental variables, we are getting the role ARN. Okay. All right. Now we have the bucket and prefix. This is where we uploaded the data last time. And let's see. So within this bucket and prefix, we have 3 folders: batch, transform, data, and model. So we have uploaded the train and test data to this data folder, right? The last time. So these are those 2 files, right? All right. So that's all we need. So we need just these 2 files to train a model. All right. So our training file, test file, it's just not much happening here. All we are doing is I'm just printing. Oh, sorry. I want to talk about this line. Okay. This is just to show you we are stitching these 3 strings together: the bucket name, the prefix, and the file. Okay. So that would give us this S3 Sagemaker course iris. This is the bucket name, this is the prefix, and this is where the data is, right? So we have created these 2 strings for training and testing files. And then we use this training input function from Sagemaker to input our training data file. Okay, so this training data file, we are simply passing it to this function so that it creates this object, that Sagemaker training input object. Now we use this train input object while training the model. Okay. All right. And then when we train the model, it's going to create some model artifacts, basically the weights of the model, etc., in the form of a zip file. So here we are specifying where do we want to write those that output to, right? So the model output, it's going to be the Sagemaker course iris and then the model. So the model artifacts are going to be stored on at this location. All right. And then so we want to train XGBoost model and the latest version of the model, right? So using this image URIs retrieve, we provide the model name, the region, and the model version. That will give us this Docker container URI. So this is the URI. So as I was saying, Sagemaker, they have installed all these libraries related to different machine learning models into different Docker containers, and then they have registered them on this Elastic Container registry. Okay, so here what we have is the container ID, the Docker, Elastic Container registry, the region name, the AWS thing, and then we will have the model name and the model version. Okay, that's how it looks like. So for any model, whether it is image classification, object detection, or text classification, or any other model, we are going to use this functionality to get the Docker URI, right? By providing the model name and the version. Okay. All right. Then, so training, it's going to be a job. So we want to give the job a name. So here we are simply saying iris -xgboost-, right? Now this job name must be unique. That's why we have imported the datetime library. So we are going to append the current date time to this string to make it unique. All right. Now, so using this estimator class, we are going to get the estimator. This is not really XGB model. This is actually an estimator. Okay. Now to the estimator, we will provide the model, the image, the Docker image, and then the role, okay, the base job name, and instance count. So these are really standard, right? I mean, this is related to the model. These two are standard. And then now instance count, only one, right? Here we are giving one. Now there are some models which can be trained in parallel, but XGBoost model, it can be trained, it cannot be parallelized. The code cannot be parallelized because the reason is we will be training one tree at a time, right? So after it, I mean, I'm assuming you know how the XGBoost model works. So we'll train a model, and then for those records which are misclassified, they get some boost. I mean, then in the next model, we'll tell the model, hey, these are important records, so give more preference to classifying them correctly, right? We repeat this process. So here we are training these decision trees or the boosted trees one after the other, right? That's why the XGBoost model cannot be parallelized, and we can train it only on one instance. Whereas if we are training a random forest model where all the decision trees, those are independent of each other, right? So in that case, we can use multiple instances to speed up the training process. Okay. And then the instance type, again, depending on our data set and how fast we want the training, we can choose the instance type. If we are training any computer vision related models, we might be using a GPU. Okay, and this is a normal CPU one. All right, then output path, where do we want to save the model artifacts? And then this is a standard variable, this volume size. So this instance will come with 5 GB. So basically this EBS, elastic block storage. So to this instance, the AWS will attach this external disk of size 5 GB, right? So depending on again our model and data set sizes, etc., we might want to increase this number. All right. And then we want to set some hyperparameters. So here we got the estimator, right? Now to the estimator, we can set some hyperparameters. Okay. So the number of classes, this is the iris dataset. So we have 3 classes. The maximum depth, this is the depth of the tree. So we are saying the depth of the tree should be 5. Otherwise, what will happen is the depth of the tree grows until each record is accurately classified, right? So that would be overfitting. So we want to prune the tree at some level. And then the number of rounds, this is the number of boosted trees. Okay. Here the objective function. Now for all the machine learning models, there is an object function. We either want to, in most cases, we want to minimize, and sometimes we want to maximize a function as well. So here we are choosing this softmax function because it's a multi-class classification. We are choosing this softmax function. Okay. All right. Then the base job name, we choose this iris -XGBoost. So here where we are getting the current timestamp, and we are appending it to make the job name unique. Okay. All right. And finally, here we are going to fit the model. So with the estimator, we fit the model, and we simply give the training input, the validation input. Now the job name, now weight is equal to true. What it does is, until this model training is done, we will wait here. So we cannot execute the other cells without this cell, or the model training is completely executed. Okay. All right. So it provides a lots of information, starting with the job name. So here it's saying, okay, I'm starting a training job, the preparing the instance. So this means what it is doing is, it's picking up one of the EC2 instances with these parameters, the size, storage, the processing speed, etc. And then it will install this XGBoost model. So it's preparing that instance and downloading our input data, the train and test data. And then finally it start the training process. So there will be lots of information depending on the model. If it's a deep learning model, it will show the epochs, etc. And the most important one would be this validation metric error. We might want to monitor this metric. Okay. All this information is written to AWS CloudWatch logs as well. We will see in another video how to access those logs and how to extract the very specific information we wanted from. For example, from this file, we want to check how the validation error is reducing with the number of steps, right, over a time. So we can extract such specific information from the AWS cloud logs as well. Now the model training is successful. Otherwise you will see some error messages. And at the end it's saying, okay, I have generated the model and I'm uploading the model back to S3. Okay. So it's uploaded the model back to the S3. That's the output part we have mentioned. The training job completed. And here it shows the number of training seconds and the billable seconds. Okay. All right. So we have written the output to this model folder, right? Now let's look at our training model folder. Our training job name. Our training job name is, yep. So it's this one, 935. Yeah. Okay. So these are the previous versions of the model I have trained. Now this is the model we have just trained. So in this path on S3, a new folder is created. Okay. New folder is created. And this folder will have the model artifacts. Now, if you look within that folder, this is how the structure looks like. And this output folder will have the zip file containing the model weights, right? So that we can use this zip file to deploy the model and make inferences. Okay. I will quickly summarize from the beginning. All right. So the important bits at this path, we have our training and test data. And then we are just doing some string manipulation so that we can get the complete path using the bucket name, the prefix, and the actual file name, right? And then we have simply used this S3 path to prepare this input object, this training input object, right? And then using the model name and the version we want to train, we got the Docker image. Okay. And then we are accessing the estimator by providing the Docker image, how many instances we want to train the model on, the instance type, and finally, where do we want to write the output to. The remaining options, those are standard, those don't change much. Okay. And we can set some hyperparameters as well. So the number of classes 3, the maximum depth of the tree 5, and we want to have 10 boosted trees. And this is the objective function we want to minimize. And then we create a unique string for the job name and we submit the job. So when we do this, on the instance we have chosen here, Sagemaker will prepare the libraries to train the model. It will download the training data and validation data and train the model. And it provides lots of information during the training. And once the training is done, it upload the model artifacts back to our S3 storage. Okay. And this is how the output folder look like. And it has these 3 folders and within which The output folder again contains the model artifacts. And in the next video, we will see how we can use these model artifacts to deploy the model as an endpoint, as well as how we do the batch inference. That's all for today. Thank you very much. In the previous video, we have trained a machine learning model to predict or to classify the iris flower type given the sepal and petal length and width as 4 features, right? So these are the models we have trained previously and using the XGB estimator. So a very quick recap. So here we have defined the XGB estimator. We set the hyperparameter. We created a job name, and then with the fit function, we have trained a model, right? So today we are going to see how we can use this model to make some inferences, okay? So the model artifacts are stored in these files. So these are 4 different models we have trained. All right. Now, because there are multiple ways of deploying the models and making the inferences. Now, today we are going to see some of them, and in the next video also, we will see more standard methods of inference. Now, the XGB estimator, we still have access to it because in the same notebook, we have trained the model. So this XGB estimator is still alive, right? So we can use this estimator to deploy the model and make some inferences, but that might not be the general case because we might not want to deploy the model as soon as we trained it, right? We might train multiple models, then deploy them, then see which one is performing well, and then one of the model we might deploy it into the production system. So at that time, we will not have access to the XGB estimator. By then, this notebook won't be alive, right? But today, we will see how we make inferences when we still have access to the XGB estimator, okay? All right. Now, first, let's deploy the model as an endpoint, okay? So to the model, we are going to give the feature values in the form of a CSV serializer. So that's why we are importing the CSV serializer function from Sagemaker, okay? And then, so using the estimator, we can simply call this deploy function, okay? Now, when we deploy a model, we need 3 things, right? One, what the model is or this estimator is. Sorry about that. And then how many instances we want to deploy the model on. I mean, this depending on the traffic, we might want to create multiple endpoints or we might want to create one endpoint with multiple instances so that if 2 users are trying to make the inference at the same time, they'll get the response immediately without one waiting for the other to finish, right? So that's the number of instances. And then the instance type. Usually we use bigger instances to train the model, but for inference, it's only doing the arithmetics on the weights, right? So we don't necessarily need a bigger instance for making the inferences. So we usually choose a smaller instance for the inference, okay? Now, this is not the best way to deploy a model because we would like to configure multiple parameters. As we discussed, what should happen when multiple people trying to make the inferences? Should it be serverless endpoint, etc., etc. Today we are making it keeping it very simple. We are going with all the default options. We are simply providing how many instances and on what instance we want to deploy the model. So we deploy the model. It creates these 3 steps. Now in the later parts of the videos, we will see all these 3 steps, how we can create these 3 steps explicitly using a number of parameters which are important for production systems. Okay, so today we are going with all the default options. Now first it will create the model. Okay, so the estimator, first it will create the model and then it will create what is called this endpoint configuration, and in the final and third step it will create the endpoint. Now I'm using the latest version of Sagemaker, but in the previous version, as soon as we train the model, like here, as soon as we does the fitting, Sagemaker used to create a model by default. So when we do this deploy, it directly used to create this endpoint config with the endpoint. But in the latest version of Sagemaker, it's not creating the model by default. So when we do the deployment, it first creating the model, then the endpoint config, and finally the endpoint. Again, don't worry too much about all these. We are going to have more videos on each of these topics with all the parameters they take. Okay, so we have deployed the model. When we deploy, we get this predictor back. Okay, we can use the predictor also to make the inferences, but again that won't be the standard practice, right? Because this predictor will be available only for the first time when we deploy it. We also have an endpoint, which is a standard way of making the inferences. We will see that in a minute. But first, let's see how we can use this predictor to make the inferences. Okay. So with the predictor, we simply call the predict function and we supply our input features, right? This is this iris flower classification model. As you know, we have only 4 features, right? The sepal length, width, and petal length and width, right? So here we are giving those 4 values to make the prediction, and we get the class as 2. Okay, we can map the class to the flower type going back to the data set, right? Now let's look at the endpoint, how we can do this with the endpoint. Because here we have not provided any name for the endpoint, Sagemaker simply take the training job name, the name we gave when we were training the model. It uses the same name for the model, endpoint configuration, as well as endpoint. Okay. But if we don't know the endpoint name, from the predictor, we can get the endpoint name back. So this is our endpoint name. Now, in order to hit the endpoint, we need the Sagemaker runtime. Okay. So using the Boto3, we will access the Sagemaker runtime. And then we use the Sagemaker runtime to invoke the endpoint. So first this is our input payload or the feature values. And then here we are hitting the endpoint using the Sagemaker runtime. The endpoint name, where do we want to hit, and what's the input format? It's a CSV or /text format. And then the body is the features. Okay. So this is what we get, the response. It contains lots of information like this HTTP headers, date, time when we called, the content formats, etc., etc. But it also contains this body. So usually this body contains the most important information. The rest of it is metadata. So within this response body, we have the predicted class. Okay, so we are just reading the body and then decoding it, because it's usually what is written is this binary string, right? So we have decoded it, so we get the class value. All right, now with the endpoint, we can make multiple inferences also. For example, here this is one flower and this is second flower. So these two we have separated by a /n. Okay, process exactly similar. Hit the call the Sagemaker endpoint using the Sagemaker runtime, endpoint name, content type, and the payload. So instead of having one record, here we are supplying 2 records. So we get 2 responses back. right? So in this case, both flowers happen to be of the same type, right? Now, let's look at, so these are two, right? I mean, this won't scale, right? We don't manually create this string, right? We might want to read from a file where we have multiple records and we wanted to make the predictions for all those records / flowers. So here we have the infer file which we created previously. Remember, this has 4 columns, 4 features. We have removed the target variable from this file. So we open the CSV file and then we get the content of this file. I'll show you how this file looks like. The same process. Okay, we call it, and this file I guess contains about 50 records. That's 1/3 of the data we used for testing the model. So we get the response. This contains the 50 classes, one for each of the input record. Now let me show you this file. Okay, as you can see here, it's just these 4 features separated by a /n. Again, next set of features separated by /n. So it's just the same as this. Okay, here we have extra spaces, but you can read the data from CSV file and you can make a string like this and make multiple inferences from a single endpoint. So this is when we have a local CSV file, right? Now let's say we have the file on S3, okay? All right, so this is where we have the file. Now there are multiple ways to read an S3 file, or the CSV file from S3. So here I'm showing 3 different ways. Now the standard and the most easy method is directly this pandas read CSV. So provided we have the AWS credentials configured, we will be able to read the CSV file directly from S3. Now the second method is using another library called this AWS Wrangler. So with the Wrangler, we will be able to access data from multiple sources, not only S3 from the databases, from Redshift, etc., etc. So this Wrangler is a more generalized method. Okay, and the third method is using the S3 client. Okay, so using the Boto 3, here we are getting the client through S3. We can also get a resource to S3. So once we get the S3 client, we provide the bucket name and the file key, right, with the getObject function or module. So we get an object back, and then the body contains the actual content of this file. So with the read CSV, we are reading the content of this file. Okay, and here with these 3 lines, we are doing just a bit of manipulation to make exactly the same string. Okay, we are using this this string buffer to read the content of the file, and then finally we are preparing this payload in the CSV text format. So this one, the output from these 2 lines is exactly the same as the output from these lines. So by this line, we have read the content of the CSV file, and then we are simply preparing the payload here. Now we can again hit the runtime, the endpoint using the runtime. We get the same response back, the 50 predicted classes for the 50 records. All right. Now we get charged from AWS as long as this endpoint is alive. The reason is because this instance we have chosen for creating the endpoint, that's reserved. So this instance is dedicated for us, and the endpoint is live. Okay, so even if we are not using the endpoint, we get charged for this instance. So for production systems, we make the endpoint live and keep running all the time because we might want to make inferences at different times. But this is for demo, right? So we can use the same Sagemaker client to delete the endpoint. All we need to do is we supply the endpoint name. So what it does is it delete the endpoint name as well as the endpoint configuration. Now throughout this process, there are a couple of things happen. Let's look at them on the Sagemaker console. Okay. All right. So when we deploy the model, as you saw, it first created, let me go back. So it did three things, right? When we deploy the model, it created a model, it created an endpoint config and endpoint. Let's see them on the console. Okay, so the first thing it did is it created this model. So if you go under Inference on the Sagemaker console, go under Inference. So the first thing it did is it created a model. Okay, so these are the different models, but this is the one which created the model. Okay, so if we go here, the two most pieces of information are where can this code run. So this is the Docker container which is used to train this model. Now XGBoost, we are using inbuilt version of XGBoost. So this container for training and inference is the same. But most of the other models, the training container and the inference containers are different. Okay. All right, this is one set of information and the second information is this. So these two things will make up a Sagemaker model. So basically the model artifacts, the weights of the model, and then where can this model run. So these two together will make a Sagemaker model. Sorry, this is model ARN. This one is the Docker container. Okay, so the Docker container plus the model artifacts will make a Sagemaker model. So the model name is this. This is when the model is created and the role which is used to create the model. And as you know, every resource or every artifact we create on Sagemaker will have its unique ARN. Okay. All right. These settings, again, we are going with the default, so nothing is here, but we can create some keys and values like which model it is, what version, for what project, maybe if we are billing to some client, what client, etc., etc. Right? That's the first thing, the model. And the second one which was created is this endpoint configuration. So whenever we delete an endpoint configuration also gets deleted. For example, let's look at one of these. Okay. So the endpoint configuration, which will have information about the model name. So we can go back to the model page we saw before, the container and the artifacts. And it will have also the training job. So if we go back to training job, then we can see lots of information like where we have, from where we use the training data and all those things. So how much time this model took to train, when did we train the model, the job name, etc. So I'll show you the important pieces. Yeah, so this is the data we used for training the model, and it will also show the hyperparameters used for training the model. Okay, and then this is the validation data. So validation data, training data, and the instance we use to train the model. These are some model metrics we can get from the CloudWatch logs. We will see in later parts of the video. And then these are the model hyperparameters. Some we set, some default. And again, we will cover all these in more detail. So here, because this model took only 90 seconds, we don't have the data to show here. But we can see here the model performance related metrics, how is the training accuracy and error, the validation accuracy and error are changing with time or the number of steps. And then we have the instance related metrics, so how much of CPU, GPU, the storage, etc. are being used. And then the logs contain all this information, and the search log is an additional service from AWS, which makes it a bit easier to search these logs. Okay, so basically this information we can search using this service in a bit more easier manner, right? So when the model takes a longer time, we will be seeing a multiple plots here. Okay, that we will cover in some other video. And here we have the model artifacts location, and finally the tags. Okay, that's the training job related information. And then let's go back. So this is the endpoint configuration, right? All right. Finally, let's go to the endpoints. Endpoint configuration and endpoints. All right. This is our endpoint. Version 1. Okay. So again, we'll cover the important pieces of information. Again, we will see the model name and the training job. The links are there, so you can go there and check. Now, this is the instance we are using for the inference. Okay, and how many instances are we currently using? We can configure the endpoint configuration so that, as I mentioned before, we can have serverless inference, we can have multiple instances, etc., etc. So all that such information will be available here. Okay. All right. This is that endpoint name, and as you see, it's a real-time endpoint. Now this data capture, so when we deploy the model, as we make inferences, we can enable so that the data we are using for inference get captured on S3 location. So this we will use for model training, so that we'll have the data used for inference, as well as we have the predictions. And when we have the actuals, for example, let's say it's a customer churn model, and eventually we know whether a customer churned or not. Then using these three sets of information, we can find out how the model is performing over the time. Okay. All right. What else? Yeah. That's it. I'm going back to the notebook. All right. So we have done all this. We have covered multiple records. All right. So we have deleted. We can delete the endpoint. Now I just want to show you this endpoint is live, right? Endpoints. So this endpoint is live. It's in service. Now from the UI also you can delete the endpoint. So go here and delete the endpoint. Okay. All right. That's for live. And then let's look at the batch inference. Okay. The batch inference means we will have a file on S3 or maybe local. We want to make the predictions for multiple files. Now this is not a live instance. So it takes up to 5 minutes to spin up the instance and prepare the model so that the inferences can be made. Okay. So here we have the batch input. As we saw before, we have created a iris infer file we have stored in this S3 location, batch transform, right? And then the output from this one is going to be another file, right? Unlike here, we don't get the response as a dictionary. We get the output as a file. Okay, so we have to specify the output path. Now, our batch transform folder, as you can see here, it has only one file called iris infer. And then using the estimator, here we are creating a transformer, right? Again, to do the batch transformer, we need to define how many instances we want to use and the instance size, right? And where do we want to save the output to, okay? Now, if imagine if it's some maybe object detection algorithm, we might want to detect objects on, let's say, 10,000 images, right? If we do one image by one image, it will take quite a lot of time. So in such scenarios, we might use multiple instances. For example, we might use 10 instances so that the transformer time or the inference time will be reduced by 10 times because these are 10 instances working independently, and the data automatically gets divided into 10 chunks, and each instance process its own chunk. Okay. All right. So we have the transformer and then we call the transform. Okay. We simply provide where is our input data. Again, the data type and the content types, etc. How we are splitting the data in this file. I mean, how the records are split. So each record is in a new line, right? So this wait function, it simply wait within this cell until the job is completed. Similar to training, there will be lots of information in the logs. So it's doing the inference, and finally, maximum payload in NB, it should have some info. So once the job is completed, if we look at in this folder, so here we chose the same path for the output as input, right? So this is our input file. So Sagemaker, it has created this output file, right? So for every .csv file in this folder, Sagemaker create a corresponding .output file. So when we do the batch transform, the path can have multiple input files, not just one file, okay? Because here we have one file, it has created this one output file with this postfix.out appended, okay? So let's download this file, csv.out file. Here we have downloaded, and if we look at the content of the file, this is how it looks like. So these are the 5 predictions for the top 5 records. Okay. All right. We have covered a lot. We have deployed the model and we looked at multiple ways of making the inferences using the endpoint, using the predictor, and also the batch transform. But this is a bit long video, but it has covered multiple ways of inferences. Okay, thank you very much. Hi, in the previous video, we have looked at multiple ways of making the deployments as well as making inferences of machine learning models using Sagemaker. We have mainly used the estimator to deploy the model, but as we have discussed, the estimator is only available within the notebook from which we have trained the model, right? But that's not the generic use case, because we might want to deploy the model at a later time in maybe a different environment for the production system, right? So today we will see how we can do that. Okay. All right. So after training the model, we have the model artifacts, right? So we have the model artifacts at some S3 location. And then we also know which instance we have used for training the model, right? As I said, in some cases, we can use the same instance for inference for inbuilt algorithms. But for if it's not an inbuilt algorithm like this XGBoost, let's say if it's a TensorFlow or PyTorch or Hugging Face, etc., the training instance and inference instances will be different, right? We will cover all those in the future videos. But for this inbuilt XGBoost algorithm, the training and the inference instance is the same. All right, so we have the model artifacts. We know where this code can run, or the Docker image, right? Now, When we deploy the model using the estimator, three things happen, you remember, right? First, it has created the model, then it created the endpoint configuration, and finally the endpoint. So today we will see how we can do those three steps explicitly ourselves. Okay. So again, I want to create a unique name for the model. So we are simply using some prefix and appending with the timestamp. Now we are going to use the Sagemaker client, which you can see from Boto 3. We can access the Sagemaker client, and this is the runtime. Okay, so use the Sagemaker client to create the model. So to create the model, we need only two things: where are the model artifacts and where that code can run, right? So this is the model path, which is where we have the artifacts. And then this is the Docker container image, right? So we are just giving it a name. And in order to execute this code, we need to supply the role ARN as well, right? So we have created a model here using the model artifacts. That's step number one, right? And then once this model is created, we can do the batch transform, right? Because in order to do the batch transform, we don't need to have any endpoints, right? So we first create the transformer simply using the model name, because we have just created the model. So we just use that model name, the instance count and the instance type, and where do we want to write the output to. Okay. Once we created the transform, we simply call the transformer with the transform, supplying the input data. Okay. So that will take about 5 to 7 minutes, as we discussed, because it's going to create an instance and prepare the model before making the inferences. Okay. All right. Now let's look at the endpoint. So first we need to create the endpoint config name, right? So here we are again creating a name for the endpoint configuration, and then using the Sagemaker client to create the endpoint configuration. So we have a name, and then here we can have multiple versions of the same model. We can make it serverless, etc. We will see the benefits of serverless in the future videos and how to do that, etc. Right? So this is version 1 of the model, and we simply supply the model name which we have created previously, and again providing the instance count, the initial instance count, as well as the instance type. Okay. So we have created the endpoint configuration. Okay. Now we are actually going to create the endpoint. Again, create a unique name for the endpoint name and use Sagemaker client to create the endpoint. Okay. And the endpoint configuration will contain all the information. So we simply supply the endpoint configuration and we just give it a name here, right? All right. So that has created the endpoint. Now it will take some time, again 5 to 7 minutes to prepare the instance, to prepare the model to download the model artifacts and to make it executable, etc. So we can use this get waiter to keep checking if when the endpoint is created, right? So the endpoint is being created, and then from this point it will be the same. So the way we create the endpoint is different, and it depends on, are we using the Sagemaker estimator, which is available within the notebooks from which we have trained the model, or the more standard method is what we just discussed. So it's this 3-step method. So in step 1, we use the model artifacts and the Docker image to create the model. Okay. And then we create the endpoint configuration, and the important pieces of information here are this initial instance count and the instance type. We provide the model name. So we have created the endpoint config, And finally, we create the endpoint name by supplying the endpoint configuration. Okay. And then the inferences, those are exactly the same. Now we can delete the endpoint configuration and endpoints from the Sagemaker client. So first we delete this endpoint name or the endpoint by supplying the endpoint name, and then we can also delete the endpoint configuration. Okay. Now sometimes we might want to delete simply the endpoint so that we don't get charged when we are not using it. And we can keep the endpoint configuration. There is no charge for keeping the endpoint configuration. Now, if we want to create the endpoint again, we can simply use this endpoint config. So we don't need to create the model and endpoint config again. Okay. So just delete the endpoint, the actual endpoint, but you might want to keep the endpoint configuration so that you can create the endpoint again. Let me show you this on the UI. Okay. Okay, let me go to the console. Okay, so as we discussed, let's say this endpoint. Now, let's say we have this endpoint config and we have already deleted the endpoint. Now we want to create the endpoint from this config. So simply open it and apply to an endpoint. Sagemaker keep changing. It used to be create an endpoint, but let me see what happens. Okay, not this one. Maybe we'll go here, create an endpoint. Okay, all right. So create an endpoint. Here you give a name, and here we can choose use an existing endpoint configuration or create a new one. Because we have lots of existing ones, so choose this option. Then these are all the endpoint configs. So choose the one you want, and then simply select the endpoint config and finally create the endpoint. So this way you can create and delete the endpoints easily without incurring any charges. Okay, so there might be a reason you might want to delete the endpoint but not the endpoint configuration. Okay. All right, that's all for today. Thank you very much. In the previous 4 videos of this course, we have looked at how to prepare the data and how to train a model and then how to deploy the models using different methods, right? We have trained a classification model to predict the iris flowers. Then we have deployed the model using the Sagemaker estimator as well as the model artifacts sitting on S3. We have deployed as an endpoint, and we also looked at different methods of inference. For example, one record, multiple records using the endpoints, and a local file, multiple records sitting on a CSV file, local CSV file, and also a file sitting on S3. Then how to create the transformer, and finally do the batch transformation, right? Today we are going to look at a Jumpstart. This is one of the most useful capabilities from Sagemaker. What Sagemaker did is they have took the pre-built models from various libraries or frameworks such as TensorFlow, PyTorch, Hugging Face, XGBoost, XGBoost, etc., etc., and they have made all those models easily available to us. Some of those models we can use them directly and make inferences. This is most often the case in the language and images space, right? For example, there are a number of object detection, image classification, text classification, or text translation models. Now we can access those models, we can deploy those models as endpoint and start using them. There are other set of models, we can even fine tune those models using our own data sets. Okay, so we will see all of those in the upcoming videos, but today we will see what is Jumpstart and what models it has and how we can use them. Okay, all right. So we have covered these libraries in the previous videos. So here we have using this drop down from IPython widgets. So this widgets, it's a Jupyter Notebook functionality which lets us do certain UI based type of things. Okay, and as we discussed before, here we are just suppressing the notebook or the Sagemaker, printing the information which is below the warnings level. Okay, this is just the region. Now, so the Jumpstart, it has a file called model manifest. It is sitting on AWS own S3 buckets. Okay, and this file this file is being updated as new models are added to the Jumpstart. We are going to just download this file and read the content of the file to see what models are available in the Jumpstart. Okay, so using the Boto3 client, we are just downloading the file. So we have downloaded this file models_manifest.json to our local directory, and then we open the file. Okay, all right. So this models list, it contains all the models. Now, as we can see here, there are quite a number of models Sagemaker has made available to us. So there are 2,700 models. Okay, so I'm just converting this dictionary or the JSON file to a pandas data frame so that we can easily view the data. Okay, so this data has 4 attributes or columns: the model ID, the version, and then some specifications related to the model, right? Here we are randomly sampling some 20 records out of these 2,751. Okay, so this model, so it's coming from TensorFlow. This IC means image classification, and then the model, the particular algorithm, it's a MobileNet version 1, and some other specifications, right? It's a classification model. Okay, now these versions, I guess, okay, this number representing this particular model version, and then this minimum version, I'm not 100% sure, because this minimum version sometimes it is lower than this current version, sometimes it is higher. Okay, and then they have some specs saying some community models, etc., some additional information, but we probably need only this information and then the version of the model. Okay, all right. So this model coming from Hugging Face, it's a Distilbert, so this is a language model. All right, so here we have MXNet, here we have light GBM model, etc., etc., right? But how we can use this model, right? I mean there are so many models, how we can choose a particular model we want, right? So here what we are doing is we are going through the model list. Now they have carefully designed this model ID so that based on the task we wanted to do, we can filter the models related to that particular task. For example, here IC refers to image classification. Then this model, it's a text to image model. So given a text prompt, it will create images for us. Okay, this is another image classification model, SPC. I'm not sure about that. Now this one is a classification model. It's for numerical data. Okay, so today we will just see how to select all the object detection models as well as all the classification, image classification models. Okay, so here what we are doing is we are just looping over all the records in this data, and then we are choosing, we are selecting this model ID, which is this first column. And as we just discussed, the model IDs or these names are carefully designed so that we can filter all the models related to different tasks. Okay. So for the object detection, the model ID, either it will have this hyphen OD hyphen, or it will have hyphen OD number one hyphen. Okay. So we are going over all these model IDs, which are some 2700 plus, and then finding the model IDs which has this specific string, either this one or this one in their name. Okay. And then we are adding it to a new list called OD models. All right. So the number of OD models, that's 70. So we already have 70 pre-trained object detection model available in the form of the Jumpstart from Sagemaker. So all these 70 models, we can use them as it is for making the inferences. If we go to the models detail page, we will know what are the objects the model has been trained on, what it can detect, etc., etc. All right. So we can use, if the models we want to detect, or if the objects we want to detect are already in one of these models, then we can start using the model right away. But that might not be generally the case. We will have our own objects. So what we do is we train one of these 70 pre-built models. Not all of them can be retrained using what is known as transfer learning, right? So AWS has a nice documentation, we'll see later, where we can find out which models we can directly use for inference and which one we can use for transfer learning. Okay. All right. So this is the IPython widget, the drop down we have created. It's a simple UI. So it just creates this UI for us. So here we are just inputting all the 70 model IDs as a list, and then a default value. Okay. And this one, this select a model, this is this just string, the description string. And then these are just about the aesthetics or the UI. So the width and some description width, etc. Okay. All right. So run this cell display that will create or that will render this IPython drop down widget. Okay. So here, these are those 70 object detection models. Okay. So some of them coming from this MXNest, a significant of them coming from MXNest. Then there are PyTorch, TensorFlow. Yeah, I guess most of these models, maybe half of them, are coming from the TensorFlow. So the TensorFlow is a framework, and then, for example, this MobileNet, the efficient.det, the ResNet, or this RCNN, all these are particular algorithms, right? Different neural networks. Whereas this TensorFlow, MXNet, and PyTorch, those are the frameworks. All right. Then if we want to choose a particular model, we can choose a model, and then this infer model drop down widget, which we have created here, we can get the value using this dot value method. Okay. All right. Let's look at one more set of models, the image classification models, right? So we are doing exactly the same thing, but this time it is this IC for image classification instead of OD and OD1 for object detection, right? Okay. All right, so here we have 162 models. This makes sense. Image classification is a more common use case than object detection. So here we have about 162 models, well, 162 exact number. And then again, we are creating a widget. And here you can see these are all the image classification models. Again, they are coming from PyTorch, TensorFlow. Yep, PyTorch and TensorFlow, most of these models. All right, again, we can select a specific value from it list. Now, either we can have this code integrated into our model training notebooks where we select the model, or we can have it separately. We select a model and then we simply start using this model in our model training notebooks. So we can keep this model selection process separate. All right, that's it for today. Thank you very much. Today we will learn how to train an image classification model using Sagemaker's inbuilt algorithm. Okay. Now, as this is a course on Sagemaker, I am assuming you already know the basics of computer vision, image classification, object detection, etc. I will try to create a separate course on the basics of computer vision. Okay. Now, for today's exercise, I have already prepared the data and created the ground truth. But those two tasks itself are big tasks and require a separate video. We will see that how to do that in a separate video. Okay, so here we have three different flowers images. This one is daisy, and this one is a rose, and this one is a sunflower. So we have a bunch of examples or images for each of these types of flowers. Okay, so at a high level, in an image classification, given an image, we will try to classify the image into one of the predefined classes, are also sometimes called as labels. Okay, if we have only two classes, we call that binary classification. Then if we have more than two classes, we call it multi-class classification. Now, sometimes each image can have multiple labels as well. For example, this image, in addition to the sunflower, it might have the daisy or rose, right? So in such a case, we will have multiple labels for each image. We call that multi-label classification, right? We will see an example of that in a separate video. So I have already organized the data. Now this is how the data looks like. The important ones are just the 4 folders called train images, train annotations. So this folder contains the images, and this folder contains the corresponding ground truth, which we sometimes call annotations, labels, etc. Right? So the ground truth, annotations, labels, these three are referring to the same thing. Similarly, we will have validation images and also validation annotations. Okay, so those 4 are the required folders. I'll just show you the data. So I'm showing it local. So train images, these are the bunch of images. Each image contain one of those 3 flowers. Okay, and correspondingly we have train annotations. Okay, so here we have this LST list file. Now different models, they take the annotations in different formats. Again, when we work with different models, we will see what input format they take and how to create that, right? This LST format, it's for the Sagemaker's inbuilt image classification algorithms. All right, similarly, we have validation images here and corresponding validation annotations in the validations folder. Okay, now this file, the LST file, it looks like this. Maybe first I'll show you for the train annotations. Okay, all right. So this one, it's a 3-column file separated by tab. Okay, so the first one is simply a serial number. We have 36 images for training, so this number, it just run from 1 to 36. Okay, and the third column, it's simply the file name. Okay, this can be JPG or PNG. Again, different images can work with different file formats. All right, and then the second column, the important one, is the actual ground truth, right, or the label. So we have this label daisy, rose, and sunflower. But as you know, computers work with only with the numbers, not strings. So we have mapped those three classes into three numbers. So the first 12 images are, let's say, class 0. That would be one of the three flowers, and then we have another set of flowers, and finally we have the third set of flowers. Now they don't have to be organized, they don't have to be like this. I mean, they can be jumbled. It not necessary that the first set of images must all be the same class. Okay, right? So this order of these lines is not important. All right, that's the train one. Now the validation, exactly the same format, but the important thing here is this one should start with 37, I believe. It's not 36, it should start with 37. I'll check if this will not have any effect, but I think it's a good idea to start this number from 37 because we have 36 here. Okay, I thought I have started this file index from 0, but that's incorrect. All right, so again, we will see in a separate video how we prepare this file. I mean, this is easy, but for object detections, this file format will be a bit more complicated. Okay. All right, so let's go back to the code. So we have seen the data preparation, some example images. All right, now I'm going back to the code. Let me just full screen. All right. Okay, so these are standard Python libraries, the standard Sagemaker libraries. Now using this get image URI, we are going to get the Docker image which has this model or the algorithm code. Okay. Now, as we have seen when we trained XGBoost model in one of the previous videos, what Sagemaker did is, for every algorithm, they have created a separate Docker image. Okay, and that image already have that algorithm code. Okay, so using this get image URI, by providing the model name and the model version, we will get the Docker URI. Okay. Now this one, it's just to suppress the unnecessary information like found credentials in the AWS config file. This is just the session and the role. Now I'm just reminding you again, if we are running this notebook on Sagemaker notebook instances or on Sagemaker Studio, we can get the role ARN just by using the get execution role, right? But since I am running this notebook from my local machine, I need to explicitly provide the role ARN. So I have my role ARN in bash profile. So I'm getting that value as this environmental variable. Okay. All right. Now this is the bucket name and data path, which is where we have stored the data on S3. I'll just show you. So we have this Sagemaker course, that's the bucket name, and Sagemaker classification LST format, that's our prefix. Okay. All right, so this is our bucket Sagemaker course and Sagemaker classification in list format. And then we have different folders for organizing different data sets. Okay. And then now here we have the number of classes and the number of training images. In my view, the Sagemaker should have learned these variables from the data we are providing, but this inbuilt algorithm, these two variables are required arguments, so we need to provide them explicitly. But there are other models which can infer the values of these two variables from the data we are providing. Okay. All right. This is the number of epochs. So the number of iterations the model should get updated or trained. And this one is the mini batch size. So what happens is, let's say we are using 100 images for training. So instead of using all 100 images for learning and then updating the weight, what the model does is it divides the number of images into mini batches of size, in this case 8, and using every 8 images, it will learn, it will update the weights, and it will do the feedback mechanism, etc. So that way model learns much faster rather than learning from all images at once and then updating the weights. All right. And then this is the instance, one of the cheap instances for GPU instances. Now the computer vision models, they require a GPU, unlike tabular data models which can work with the CPUs. Okay. Now here I have provided a link. Maybe let's go to the link. So here you will see the price. So for training instances, a different price. For inferences, different for price. The batch or the data processing, etc., etc. Right. So today we are looking at training. Now all these are generic CPU instances, and these ones computer optimized but still CPU. Now these ones are GPU instances. Okay. Now, depending on if we are doing transfer learning or how much data we are using for training, we might want a bigger instance. But for this model, the images are just 36, and those are extremely low resolution, really small size images. So I'm using, I think this instance, which is the cheapest one. Well, this one. 4 and 32. Yeah, this one. ML G4 DN X large. Okay. So it cost about 0.7 US dollars per hour. Okay. All right. Let me go back to the code. All right. And then we are defining a prefix for the job name. So the first thing, we want to get the Docker image, right? So using this image URIs retrieve, here we provide the model name and the model version. So we want to train an image classification model. This is an inbuilt algorithm by Sagemaker. But if it's from other library, we typically have the prefix, maybe TensorFlow, PyTorch, Hugging Face, etc. Right? And in most cases, we probably be using the latest version. But if for any specific reason you want a specific version of the model, you can provide the version here. Okay. Region, that's a default parameter. Now, there are two values per the scope. One is training, the other one is the inference. This point is very important because it will determine how we deploy the model. Okay. Now for the inbuilt algorithms, the same instance is used for both training as well as inference. Whereas if it's from a third party algorithm, then the training instance and the inference instance will be different. And for those, we also need to provide what's our endpoint, the model artifacts as a zip file that we will cover in the next video. But today we are using the inbuilt algorithm. So it makes a lot of things easy for us. Okay, we don't need to provide any entry points, the model artifacts, I mean the source model artifacts, etc. explicitly. We just need to get the image URI. Okay. So this is that image URI. So basically this is the ID, Docker, ECR means Elastic Container Registry. This one is our region name. and then this is the standard amazonaws.com, and this is the model image classification, and this one is referring to the latest version. Okay, now don't worry about this message, because this function is so generic, and the parameters it takes, they depend on what we are trying to do, right? For example, if it's a tabular data, we don't need GPU. Maybe if it's a again, if we need GPU, the information here will be slightly different. Okay, but don't worry about it. All right, and then we need to define a path where we want to write the model artifacts. Okay, that's the path. So within the same folder and prefix, we are asking SageMaker, hey, create a new folder called model output and store my model artifacts there. All right. Then we are defining this SageMaker or the classification estimator. Now the important, by providing the image URI. Okay, the image URI, which is this. All right. And then standard ones, role, the instance count. Again, if this model can be trained in parallel, we might use multiple instance. A good example would be random forest, where the trees are trained in parallel, right? Now the training instance type, which we have discussed before, and again, a couple of these parameters are really standard. So this is the external EBS volume size, the file mode. Now this estimator can take the data in different formats. For example, there is a record IO format. TensorFlow has its own format, etc. But we will work with the file format so that we can, it's easy. Now, when we have large data sets, really large data sets, the record IO, other formats are more efficient for reading large amounts of image data. But typically, when we work with our custom data sets, and we will be using the transfer learning, meaning we will be training only for a few steps using probably not more than 1,000 images. The standard file format also works fine. So it won't make much difference reading the data time. Okay. And this is the output path in the standard session. Now, here we set the hyperparameter. So as we discussed, the number of classes and the number of training images. So this first one and third one, these are required parameters. But for some other models, the SageMaker or the models, they directly interpret these values, this value from the ground truth file and this one from the images folder. Okay. But for this inbuilt algorithm, we need to provide these two mandatorily. And here we have the number of epochs and then the mini batch size. Now, this one is the most important one. Here we are saying use pre-trained model is equal to 1. What that means is we are saying I want to do transfer learning. So what it means is, now this resonance model has 18 layers, right? So when we say we want to use transfer learning, the first 17 layers and their weights are frozen. Frozen means those weights don't change during the model learning process. So what happens is the 18th layer are also called head layer. It's removed from the neural network architecture, and then a new layer is created with the number of nodes equal to the number of classes. So what happens is the output from these 17 fixed layers, it gets fed to the final layer, which is where the classification happens. So all the learning process of finding the patterns in the images, finding the features, curves, etc., the specific things related to different classes, etc., happens within the first 17 layers, and the last layer only the classification happens, right? So for that reason, we can use only few images, and also the number of epochs can be a few. Okay. Whereas if we are training a model from scratch, we might be requiring tens of thousands or even hundreds of thousands of images, which is what they have done when these original models are trained, and the number of epochs will also be quite high. Now again, don't worry about most of these parameters. Those are standard and default values. The learning rate, probably you can play with the learning rate. So choosing a high value, the solution jump from one what is called local minima to another local minima. So the solution don't converge to its best state, which is global minima, right? Now, if you choose a small value, the number of epochs are it will take quite more time for the solution to converge. Okay, that's learning rate. Another important parameter, this multi-label one. So as we discussed, an image don't necessarily be labeled or mapped to just one label. It can have multiple labels. For example, one of the flower images we saw, it can have both, let's say, daisy as well as rose, right? So in that case, the image has two labels. So for that, we will set it to 1, and the ground truth format will also be different, that we will discuss when we train a multi-label image classification model. Okay. All right. Here we are just setting some paths. So as we have discussed, we have a bucket, we have a data path, and then we organize the data into 4 different folders. We have training images, training annotations, validation images, validation annotations, right? So we just define those 4 paths here. And then the Sagemaker has this method training input. So we simply supply these paths here, right? So here we are saying, okay, train images, that's of type training input, and here we are supplying the S3 path where we have the training images, and then this will change depending on the data format. Here we are saying it's application JPEG. There are a couple of formats like X image. I think that will work with JPEGs, PNGs, etc. So that's probably more generic. And then the data type S3 prefix, right? So for all the image related projects, in most cases, these 3 will remain the same. We just provide the paths. Okay. So those are the 4 paths we have provided. And we have the 4 variables in this training input method or format. Okay. And then we are simply creating this data channels with the 4 variables. So here we have train. Now these are important. The key values should be exactly the same, because when we train the model, when the data from all these gets downloaded to the training instance. So as you know, the training is going to happen on a different instance, right? So this notebook or this instance, it's just acting well, from here we are executing only some commands, right? But there is a separate instance where the actual training happens. So the data from S3 gets downloaded to that instance, the training happens there, and the model artifacts from that instance are copied back to S3. Okay, so when that instance try to download the data, it will look for these key values. So these 4 key values are very important. And I find some models, they have slightly different key values. For example, I think TensorFlow model, it requires training as a keyword, not just train, right? And it don't require this LST format input. Okay, and we'll see that in the next video. All right, and then we have a job name prefix. So we are creating a unique job name just simply by appending the current timestamp, right? And that's it. We are simply fit. So this fit method, just like in scikit-learn, it will train the model. Okay. So yeah, it's saying, okay, I'm going to train a model with this job name, and it will prepare the instance using that algorithm or the Docker image. It will download the data, it will verify the data is in the right format, etc. And it will train the model. Provide quite detailed logs. in one of the videos, we will see how to analyze this, how to access these logs from Sagemaker CloudWatch logs, and do some plotting, etc. But one of the most important ones for these deep learning models is this epoch value and this validation accuracy. Okay, because we are training this model for 10 epochs. So here we have this final, the validation accuracy, some 87%, right? So the model has trained and the artifacts are uploaded back to the S3 location output path, and that complete the training job. Here it will show you the billing seconds. Okay, the training and billing seconds, often these values are very close. All right, so we have trained the model. Let me show you. Control. So we have defined the model output, right? So these are all different models I have trained. So let's look at one of the recent ones. Maybe this is Jumpstart TensorFlow inbuilt ResNet. Yeah. So this is how it looks like. Profile output. Once again, it should have 3. Maybe that one failed. Okay. I was expecting another folder called output. So not this one. Profile output. Okay. Maybe let's. Okay, this also has 2. Yeah. So if the job is successful, it will look like this. Okay, there will be this additional this is the important folder output. Here is where the model artifacts are. Okay, so our bucket name, the prefix, and this is our output path, model output, and then it will create a folder with the training job name, and then it will have multiple folders in it, but the important one would be this output, which is where the model artifacts are stored. All right. Now, that's how we train a classification model using Sagemaker inbuilt algorithm. Now, we'll quickly, the focus of this video is not deploying our inference, but I will quickly show you how we do that, right? So if we want to do an inference, obviously we need to define an instance type where we want to run the inference. We need to create the model. So we have created the model artifacts, right? Now we need to create a model name. We need to create an endpoint config and endpoint, right? But we are deploying the model directly from the estimator. So when we do that, the Sagemaker, it automatically create a model for us, and then an endpoint config, and finally an endpoint. So which is what happening here. So we simply provide how many instances we want for inference and the instance type, and we are supplying the endpoint name and the model name. So, okay, so this one, the estimator, it already know which image to use for inference and where the model artifacts are, because we are still working within the notebook, right? And then it will create these 3. Okay, so we have created an endpoint. Now, in order to make the inferences, we'll have the Sagemaker runtime client. So using this Boto3 client, we're accessing the Sagemaker runtime. Okay, Sagemaker runtime, and then we can invoke the Sagemaker runtime by providing the payload, which is image in this case. So here I have an image, local image. Okay, so just read the image and convert it to bytes array. And now we are calling this endpoint, and this this can take the input in the image JPEG format, and the output will be this JSON format. And then this is the actual image content, right? Then we get the response back. The response will be standard Python, the Boto3 SDK format. It's a complex dictionary with lots of metadata information, etc., etc. But the prediction we are looking for, it will be in this response body. It will be again in this binary. We are just decoding that binary string. So we get the probability for the three classes. Okay, so the first one is almost negligible. The model is very certain that it belongs to class 1. So let's say this is class 0, 1, and 2. The class 1, we can map it back to the name or the string. It will be one of those 3 flowers, right? And as we discussed before, we get charged for these endpoints because those instances are dedicated for us. So even if we are not doing any inference, we get charged. So it's important we delete the endpoints. Okay, so when we delete, the model don't get deleted. So when we deploy, 3 things are created, right? The model, endpoint, config, and endpoint. So when we delete the endpoint, only the endpoint and endpoint config gets deleted, but the model we created, it will remain there. Okay. Yeah, so as we discussed, as I said, the focus is not so much the inference, the model training. Probably already a quite long video, but in the next 3 videos, we are going to train another image classification model using TensorFlow, and then an object detection model, again inbuilt algorithm as well as TensorFlow. The process will be very similar, so you get used to it and it becomes clear, and you will start to see the patterns, how Sagemaker standardized the model training process, so that when we know how to train one model, training other models also becomes easier. Okay. That's all for today. Thank you very much. Previous video, we have looked at how to train an image classification model using Sagemaker's inbuilt algorithm. Today, we will train the same image classification model but using TensorFlow and transfer learning. Now, before watching this video, please watch the previous one, because some of the important concepts we have covered in detail in the previous video, we will skip those concepts in the present video. Okay, so please watch the previous one, then only you will be able to understand this video. All right, first let's start with the data preparation. So for the inbuilt algorithm, we have the training images and the corresponding training annotations in the form of this LST file, right? And similarly, we had the validation images and the corresponding validation ground truth file. Okay. It's a little easier using TensorFlow because the way we are going to organize the data is slightly different, so that we don't need this LST file. Okay, so that was using the classification using the LST format and inbuilt algorithm. But TensorFlow uses the subfolders. What I mean by that is, so within this train images, we will organize the images such that the images belonging to each class are in a separate folder. So these are all the images of Daisy, and then these are all the images of Rose, and then Sunflower, right? So this way, we don't need to explicitly create an LST file, right? As we have seen previously, the LST file, if I might open here, yeah, it essentially have this information that each file, the class label, right, in the form of these integers. But we can organize all these images into one folder, and then all these images into another folder, and finally these images into a third folder, so that we don't need to create this LST file, right? So that's what the case with the TensorFlow algorithm, right? So we don't have the annotations or the ground truth folders. Okay, that's one main important difference. Now this works when we have only one class for each image. When we have multiple labels, which is called multi-label classification, this method don't work. So in that case, we again need to explicitly create the ground truth or the annotations file. Okay. All right. Let's jump into the code. Now, the code for all these videos are provided on GitHub, and these are some important URLs from Sagemaker blogs as well as the Sagemaker GitHub. All these links are provided either in the notebook or in the description below. Okay. All right. So again, some of the important concepts we have discussed in the previous video. We don't cover them in detail. We will be contrasting this training of this model, which is not inbuilt, with the previous one, which is inbuilt, right? So it's important you watch that video first. All right. Okay. So in a previous video, we have used only this functionality to get the Docker image, the training Docker image, and also the training as well as inference image are the same for inbuilt algorithms. Now this algorithm coming from TensorFlow, we need to explicitly provide the model artifacts as well as the training script. Okay, I'll show that in a minute. So we have seen the hyperparameters, the estimator things before. So this can be removed. I am loading it separately. All right. So let's get to the important or the main differences, right? So as you can see here, we don't have the number of classes and the number of training images explicitly defined, okay? Which was the case when we use the inbuilt model. Here, our data path is different. The bucket is the same, but this time we organize the data into these subfolders, right? Which is this one, the subfolders. Yep, the subfolders one. All right. So, okay, it's not TensorFlow today. It's a PyTorch model. So we are going to train this image classification model using the PyTorch framework, and the algorithm is this MobileNet version 2. Okay, and we want to use the latest version. Now, here as you can see, there are these three things we are retrieving, right? So we are retrieving the Docker image. We are retrieving what is known as source URI. This will contain the entry point or the entry point, the Python script. And then this will contain the model artifacts, the pre-trained model artifacts. Okay. All right. So again, here we simply supply the model ID, which is this PyTorch MobileNet version 2. And then the latest version. Now the image scope is training. Okay. Because for these non-inbuilt models, the training and inference images are different. So we need to provide the scope as well. Okay. All right. And then this one is the train instance type. Again, I think we are using this cheapest instance, GPU instance available, right? So that will retrieve this Docker URI. Okay. All right. So as you can see, this one, it's a PyTorch in the training mode, the model version, and it's GPU and Python 3.8 version. Okay. As we discussed, image or computer vision models, they require GPUs. Then we are retrieving this, what is known as the source URI, right? This basically contains the entry point. Okay, so that will look like this. So within this source directory, there will be a Python file called entry underscore point dot py. Okay, right? That will contain the code for training the model if we are training, or for inference if we are doing the inference. And then this third one, again we supply the model name or the ID, the model version, and the scope. Okay, this will extract the pre-trained model artifacts. So this one, right? So this is very similar to the zip file which is created after we training the model on S3, right? But this contain the model weights as they are, right? Again, if we are doing the transfer learning, we are going to update the last layer and it waits for our own training data. Okay. Again, to quickly summarize, if it's an inbuilt algorithm, we just need to retrieve the Docker image and we don't need to worry about the pre-trained model artifacts as well as the entries script. Whereas if it is not a inbuilt algorithm, we need to extract these two explicitly, right? That's the main difference between training an inbuilt algorithm versus not an inbuilt algorithm. This is very, very important. The reason I'm stressing is once you know this difference, the process is very standard, right? Whether it is object detection or text classification or maybe image generation or maybe even numerical data, right? So the process will be very similar for inbuilt algorithms, and it will be very similar for non-inbuilt algorithms. Okay. All right, we extracted those three variables, and then for the model we have chosen, we can extract the default hyperparameters. Again, we simply need to supply the model. So everything depends on the model and its version. So we have extracted the default hyperparameters, right? Then we can change them. We can update if we want to do for, let's say, more epochs, etc. So for example, this model, it has only these few hyperparameters. So by default, train only top layer. So this is what we are referring to as transfer learning, right? So we are training only the top layer, right? And then the number of epochs. So here we have explicitly set the number of epochs to 5. So we have modified a hyperparameter. Again, the learning rate, the batch size, if we want, we can change. Reinitialize top layer. So we are just keeping, I guess this one, the previous layers, the weights as it is. Then here we are setting the output path, and then the process of choosing this estimator and the rest of it will be pretty much similar for any model we train with Sagemaker. Okay, so the default role, the train image. In addition to train image, we are supplying these two image URI, model URI, source directory. Yeah, so these three information, right? So basically the source directory, this contain the entry script or the entry point script, which is the transfer learning.py, right? So this source we have extracted from here. So this is also a zip file and it contains that entry file. So you can unzip this file and you will see one of the files is this transfer learning.py. Okay. And the other one, model URI, which contains the initial model weights. This is that one, right? So this additional information we have extracted, we have supplied in the form of these three variables. The model initial weights and the source directory, which contains the code what to do, and that file name is transferlearning.py. Okay. These are standard again, as we said before. So instance count and the instance type, and we are setting these hyperparameters from here. And finally, the output path where we want the model artifacts. Now the data channels, it's different because our data format or the data organization is different, right? So this time we don't have any ground truth files, right? Now this is not necessary. For some, even appending this slash at the end of the path is necessary. That will be the case for object detection models using TensorFlow, okay, which we will cover in the next or the video after. So we are simply defining these two paths. Where are our training images as well as where are our validation images. We don't need to provide the ground truth because we have organized the data such that each folder contain only images related to that particular class. Okay, so that's our data channels. And then again, get the timestamp and define a unique job name. So it's this flowers classification. It's Jumpstart TensorFlow. Okay. Then we simply fit the model. So we just need to supply the data channels and then logs is equal to true. I guess this will write the logs here and then the job name. So this is the job name. So again, this format will be the standard. So it just says, okay, I'm going to do a job with its with this name, and I'll prepare the instance. I'll download the required data and then start training. Okay. All right. So it's unlike the previous model, we have a little bit easy way of accessing the information. So towards the end, it's displaying the training and validations accuracies during each epoch. Okay. So this is the best accuracy. The job is completed, training and billable seconds. Okay. So it did not explicitly say I have uploaded the model artifacts to the output folder, but it has done. If it's saying the job is completed, that means it has done that. Now, as we discussed, as this is not an inbuilt model, the process of deployment is also different. Okay. So we start with inference instance. Now this don't have to be GPU because during inference, there will be only very few calculations as compared to during the training. So for training, we need GPUs, but for inference, even small instances which can fit the model into its memory will be able to do. Now, so the inference image or the Docker is different, right? That's what we were discussing. So now this time it's same as before, but this time image scope is different. So for the inference, the Docker image is going to be different from the image which we used for training. This one, right? So this is the case for non-inbuilt models. Whereas for inbuilt models, same Docker is used both for training as well as deployment or inference. For non-inbuilt models, it is different. So that's why before the model deployment, we need to get the image URI for the inference for the model and version we have used for training. Okay. All right. And similarly, the entry point will also be different. Okay. So this time it will be inference.py, whereas earlier it was transferlearning.py, right? Now, what about the model URIs? See, this time we are not retrieving the model URI. You know why? That's because we have created a new model with new weights, and that file is already on our S3, right? In that output path we have specified. So that's why we are extracting only these two variables, the train image URI and the inference script using this source URI. We don't need to extract the model URI because it is already sitting on our S3. Okay. So again, we can have some model name, endpoint name, or we can leave it default. So in that case, it will use the job name for model name, endpoint, and endpoint carving name, right? Again, the focus of this video is not inference, but just to show you that the model we train is working. So here we are using the estimator to deploy the model. And unlike before, we need to provide the entry point script. And in addition to the image URI, this is the image URI, we are also providing the source directory. And these are just names and the instance type, right? So the three standard things: model, endpoint, endpoint creation, that will create an endpoint. And then in order to do the inference, we are accessing the Sagemaker runtime, just opening an image. This is slightly different for different models. Some models take this bytes array, some models takes the image as it is. So so just invoking the endpoint with its name. So we can identify each endpoint just by using its name. And then this is our image payload, right? So this time the response is much more user friendly. Now, when we trained using the annotations file like this, it does not contain information about what the class name is. It contains only the class IDs. So the model has simply returned 3 probabilities for each class. Whereas this model is reading the data from folder structure like this, it takes the folder name as the class name. Okay. Now, because we set this response to be verbose, it has provided in this nice user-friendly format. By default, it will only return the predicted label. Okay. So because of this verbose, now it has provided the probabilities for each class and the labels we have, the 3 labels. Okay. And finally the predicted class, which would simply be the one with highest probability. So in this case, the first one, I probably organize probably either this order is fixed or it will return such that the first one always contain the highest probability. Then in that case, the order of this labels will change. Okay. Again, make sure you delete the endpoint to reduce the cost. All right. So we will have follow-up videos where we will do the batch inference and we will get the predictions on all the validation images, and we will access this information for each image. We'll compare against the ground truth. We will compute various validation metrics such as confusion matrix, the precision, recall, etc. etc. Okay. That's all for today. Thank you very much. In the previous 2 videos, we have learned how to train an image classification model using Sagemaker's inbuilt algorithm as well as PyTorch framework. Please watch those two videos first because the process for training object detection model will also be very similar, right? So few things change like the data preparation, the ground truth format, etc. But as far as the training steps are concerned, they will be very, very similar. Okay. All right. Now, again, I'm assuming you know what is object detection because this is a course on SageMaker. I will try to create a basics computer vision course, okay, where I will explain what these different tasks are. Now, in object detection, given an image, we try to identify the objects of interest, right? So image classification is at the image level, whereas this object detection, it's much localized. So in addition to knowing what objects the image has, we will also know where in the image the objects are. For example, let's take this image and we are interested in two objects, cat and dog. Okay. So this image has 4 objects, 2 cats and 2 dogs. And we also have these boxes to indicate where in the image the objects are. Now there are various ways to have these box coordinates. Some models, they'll have this top left, top corner and bottom right corner coordinates, top left and bottom right coordinates. Some models take the center of the box and then these half widths, etc. Right? So when we work with different models, we will cover all of those details. But today we will be training an inbuilt model called SSD, single shot detection. Okay, so this model, it takes the top left coordinates x and y, these two numbers, and then bottom right coordinates x and y, two numbers. Okay, now I have already prepared the data. Again, the data preparation, ground truth preparation, etc. we will see in the follow-up videos. But first, we are trying to become comfortable with the models training. We have seen this for tabular data using XGBoost model. Then we have seen image classification models using inbuilt and different frameworks. And today we are looking at object detection using inbuilt. In the next video, we will do the same object detection, but again using either TensorFlow or PyTorch framework. So first, we are becoming comfortable with this model training for tabular data, text data, images, etc., etc. Then you will start to see the patterns, right? So once we become comfortable, then we get into the data preparation part, and after that, the model validation part. Okay. All right. So I have already prepared the data now. So object detection SSD model. Now train images, it has all these images, and then we have train annotations. Now the SSD model, it expects one JSON file for each image. Okay. So corresponding to each image in the training folder, we will have one JSON file for each image. Similarly, we will have validation images and then the validation annotations. Okay, so those are the 4 folders. Now let's look at what is in one of these JSON files. Where is my VS Code? Yep. All right. So this is one of the JSON files. So this format is particular for SSD model only. Now, if we are training the same SSD model using TensorFlow, the format might be different. Maybe for PyTorch, it will be different. it essentially contains the same information, but how we measure the box coordinates will be different, and it might not have the label names. It might contain only the class IDs or label IDs. Okay, but let's not worry. Let's look at what it takes for SSD model inbuilt. Okay, so this contains 4 attributes. So the first one is file, which is basically the image name. Now this is the corresponding ground truth file in JSON format for this image, right? And then we have image size. It takes 3 values: image width, height, and the depth. Now for color photos or images, it will be 3. If it's gray images, this will be typically 1, but we mostly work with color images, so this value by default is 3. And then we have annotations. Okay, now this is a list, and the list contain as many elements as the number of objects the image has. Okay, so for example, this particular image, it contained 2 objects. Okay, so this is object number 1 and this is object number 2. Now it just happened that both objects are same for this image. Now for the dogs and cat images we saw, it has 4 objects and 2 objects for each class, right? So an image contain any number of objects belonging to any number of classes. Okay, it may contain only one object or it may contain multiple objects. So in this case, each element within this annotations is an object with 5 elements, right? So the first one is this class ID. Again, this is an integer index starting with 0. And then we'll have these 4 values as the box coordinates. So SSD model is taking the top left and bottom right coordinates. So the top and left. Okay. And then, sorry, it's not taking the bottom right coordinates. From the top left coordinates, once we know the coordinates, we can identify the box using the width and height of the box also, right? So for example, let me go back to the image. So, okay, sorry, I was wrong. So the SSD model, it takes this top left coordinates. So this point, once we know this point, in order to know the box, there are various ways, right? I mean, we can know this coordinate, the bottom right coordinate. Then we can draw a rectangle, or we know this coordinate and then we know the width and height of the image. So the width in this X direction and the height in this Y direction, right? So using such information also, we can construct the box. So that's what the SSD model is doing. Top left coordinate and then the width of the object and height of the object. Okay. And then for the second object, we have the same 5 attributes, the ID as well as the coordinates. And finally, it has these categories, which is simply mapping between the class IDs to the class name. Okay. All right. So in this case, both objects belong to the same class ID, which is the daisy. Okay. I'll just show you the image as well. This is that image. So we have 2 objects, right? So one bounding box here, another bounding box here. We actually have a third object. I mean, same daisy flower. It's not fully visible. It's up to you. I mean, sometimes we might draw a box as well, even though it is not fully visible. Yeah. All right, so that's how we create the ground truth. Okay, so we have the images and we have the ground truth JSON files, one for each image. All right, let's go to the code. Now, okay, So here we define the bucket name and path. And similar to classification inbuilt algorithm, the inbuilt object detection algorithm or model also expects the number of classes as well as the number of images for the training, right? Other frameworks, we don't need to explicitly provide these variables because from the JSON files and from the images, these can be computed inbuilt, right? All right. Then we have the number of epochs and batch size. And we have the training instance type and a job name, right? So these are the variables. Now you see the similarities, right? Whether it is classification or object detection. I have tried to simplify the code. We are trying to train the model with as few commands as possible and have standardized so that you will see the the similarities between these four models: two classification models, two object detection models, inbuilt, non-inbuilt, right? So that way you start to see the patterns and it becomes easier to do the training. All right, now we are retrieving the image. This time it is object detection, okay, and very standard, the training and also latest. Now even if you don't give this variable, I think it will take the training as default. Again, as it is an inbuilt model, the same Docker is used for training as well as inference. Whereas for non-inbuilt models, these two are separate. These two are different. Okay. All right. Let's define the output path, and then let's get the Sagemaker estimator, object detection estimator. So we simply supply the Docker image, and then everything standard as before, nothing different here compared to the classification one. So the role, the instance count, the type, the size, memory size, this is the maximum run. Now if you don't set this value, for some reason, let's say the algorithm is not converging, or maybe there is some other issue, the model might keep running and we'll get huge bill. So this, I think in seconds. So once this time limit is reached, the training automatically stops. I'm guessing, I'll make sure that is correct. Okay. The input mode, again, file format. We discussed before, there are multiple ways. One of them is record IO, which is very efficient for loading large amounts of data. But again, we will be doing transfer learning and our own use cases won't have millions of images. So probably the file format works as efficiently. Okay. And then the output path. So only the 2 or 3 variables here. The train image, this will change from model to model. Then we have the output path changes, and then 2 attributes related to instance. The rest all are fixed for any estimator, right? Now then we set the hyperparameters. As we have discussed before, we need to explicitly define the number of classes as well as the number of training images, right? And then the number of epochs and batch size. Now this SSD model, it can use 2 frameworks or algorithms. So the SSD, it works like it's a 2-step process. In the first step, it get the features from one of the existing models. The one is ResNet. What's the other one? Is it? I'll find out the other one. Okay. So it will take one of the 2 values, and then the pre-trained model. So this again, one indicates the transfer learning. Okay. All right. So these all, we can leave them as it is. I mean, the Sagemaker blogs and notebooks, they probably find the most fine-tuned parameters, so we can use them as it is. Okay, and then here we are defining the paths for the input or the training data annotations, validation data and annotations. This we have seen. This is exactly similar as before. Okay. All right, then here we are defining the data channels, which will contain these 4 attributes: train images, train annotations, validation images, and annotations. Again, create a unique name for the job, and that's it. Train, submit the job. Okay, supplying the data channels. Now these two are not required parameters, but we would like to give a job name, so that maybe later we can identify, we can search in the console. For example, okay, what are the models I trained in maybe the first week of June, something like that, right? All right. Okay. Again, the logs follow same format, starting with the job ID. Prepare the instance, download the training data, download maybe the model parameters if it's not available there, using other frameworks. Again, lots of information. The most important one, we'll see the validation score with the epoch number. So it will be quality metric, post metric, folks. Let me find one. It has lots. Okay. So this is for each epoch, start time, end time, some blah, blah, quality metric. Yeah. Yeah. So quality metric, train, smooth. Batch for cross entropy. It used to have validation MAP. Yeah, here it is. Okay. So at epoch number 9, this validation MAP, it's just 0.02, which is very, very poor. Now, this the data set. Okay, let me show you this. So as you can see, these images are extremely poor resolution. Those are just in tens of KB. This data set is not really suitable for object detection, but I just want to train a model quickly with low cost, and the main purpose is to show you how to train the model rather than to train a good quality model, okay, or most accurate model, right? So this is not a great model, and also we probably need to train for more epochs if the objects look somewhat similar to each other. In this case, the daisy and sunflower, when seen from far, they look somewhat similar. And also we have very, very few training examples, and the flowers have multiple colors, so the training data is probably not sufficient. Okay. All right. So the job completed, and again you see the time. All right, so that's how we train an object detection model. Now the rest of it, quickly deploying the model and making one inference. This is exactly same as before, so I won't go into the details. But the prediction, it looks like this. So it's a list of lists. Let's look at just one element from it. So this is the first element or the first detection. Okay. So the first element, even though it is a float, this is actually the class ID. So for our case, this can either be 0 or 1 or 2. Okay, because we have 3 different object types. And then this one, the value will be between 0 to 1, and that's the confidence score. So higher the confidence, close to 1, the model is very confident that the object is what it is, or the prediction. So here the confidence score is 0.38. That's really poor. And this list is sorted using this second element. For example, if we look at the second detection, the score, as you can see here, this is 0.381, whereas this one 0.384. So as we go down the list, the confidence score of the detection decreases. Now generally for object detection, there will be lots and lots of detections with very, very low confidence score. So what we do is we choose a threshold. It could be, let's say 0.3, 0.5, something like that. And then we ignore all the detections below the threshold. So 90% of the detections will have very, very low confidence score. Okay. So, all right. And then there will be 4 values. These are the box coordinates. Now earlier we have seen in the ground truth as integers, right? But this time we have the fractions because these are scaled coordinates. Okay, so these values are between 0 to 1. So these are scaled using the image dimensions, right? For example, it will be something like this. For example, let's say this coordinate is 50 and the image size is, let's say, 100. So it will be displayed as 50 by 100, 0.5 rather than 50. Okay, so that's why we see the fractions here. Now, in the follow-up videos, we will access this information and we will compute the model performance matrices, and we will use these numbers to draw the detected boxes on the images. We will also draw text on the image with the label, ID or name and the probability, etc. So that on the image we can see where the detections are, what the detections are, and their confidence score. Okay, we will do that in the follow-up videos. But I will quickly summarize. So first we prepare the data into train and validation. We have the images and annotations. We have one annotation file for each image, and then the annotation file, it takes this format. So basically the file name, the image size, and then annotations contain the object's information, what object it is, and where in the image the object is in the form of this top, left, width, and height, right? Different model takes different formats. And then because it is an inbuilt algorithm, the process is so much easier. So we simply supply, okay, I want to do an object detection using the latest version of the model. So we get the image URI, and then we define the output path. We get the estimator using the train image URI. We also define how many instances we want to use for training and what instance, and we supply the output path. And then we set some hyperparameters. So these are mandatory hyperparameters. The number of class, well, these are not really hyperparameters, okay? The hyperparameter is something which can affect the performance of the model. This, we just need to supply the number of classes and the number of samples or the training images. These two are not hyperparameters. So the epochs and mini batch size, they are hyperparameters, okay? And this base network, to extract the features, it takes 2 values. One of the 2 values, one is this ResNet 50. The other one I will check and maybe explain. Well, I'll mention that maybe in the comment section, but I think it's mobile net. So the pre-trained model, this is for transfer learning, and we can leave the rest of the variables as it is. And then we define these data channels by providing the 4 paths. We create a unique name for the job and simply submit the job. Okay, the inference is exactly the same, whether it is classification or object detection, etc. All right. So in the next video, we will see how to train an object detection model using one of the frameworks, either TensorFlow or PyTorch, etc. Okay, that's it for today. Thank you very much. 3 videos we have looked at training image classification models using inbuilt algorithms and also other frameworks such as PyTorch, right? And then we looked at training object detection model using Sagemaker's inbuilt algorithms. Okay, today we will train an object detection model using the same SSD single shot detection algorithm, but the TensorFlow framework. Okay, all right. Please watch the previous 3 videos. They cover almost all the concepts. So in this video, we'll try to keep it short and we will cover only what is different. Okay. So as you know, object detection, we try to identify the objects within the images, and each object we identify using coordinates in different formats, right? So let's start. Okay, here I have already prepared the data. Now this is again different. So for the 4 models we are training, the data format is different. Okay, so for this one, we'll have the train channel or the train path. It should contain this annotations.json file and then another folder with name images, and our training images are here. Okay, so it will take this train path. There should be 2 things: one, the annotations file, and then the images. Now this is different from inbuilt Sagemaker model, right? Where we have, let me see if I can show you that. All right, where we have the train images as well as train annotations, and we had one file for each image. Whereas for the TensorFlow model, the input format is different. We have the images and then a single annotations file. Both should be sitting in the same folder. Okay, all right. Now let's look at the format of this file. Okay, this is for inbuilt SSD model, which we have looked into it in detail. But now for the TensorFlow, this is how it looks like. Okay, so here we have, it has 2 elements, right? It's JSON file. First one called data, and it contains the number of elements as many as the number of images. Okay, so the first one, the image name, the height and width of the image, and then this ID. Okay, so this ID is just the serial number. Okay, so if you are comparing with this file, so basically the data part contains the image name and then the width and height of the image. We don't need to provide the depth, but it contains this serial number as this image ID, right? So that's the data part. And then it will have the annotations part. Okay, so the dictionary contains 2 keys, data and annotations. Now the annotations, it will contain the image ID. So this image ID is to map the information between annotations to the data. Okay, and then we have the box coordinates. Okay, same as before. So the top left coordinates, and I think then the width and height. Okay, and then the category or the class ID, which is either 0, 1 or 2, because we have only 3 types of objects. Now as you can see, this format do not contain the class name, right, which is for inbuilt SSD model. Okay, it contains only the class IDs. So that's how we prepare the file. Now the reason why this image ID start from 36 is because this is the validation file. So we have the 36 images for training, and the train file contain the index from 0 to 36. I believe 1 to 36. Again, this is incorrect. It should start from 37. Okay. So when we have such conflicts, Sagemaker probably ignoring such images and the corresponding annotations. All right, let's go back to the code. Okay, so we have prepared the data. And then is this is inbuilt? Okay, all right. Yep. So as we were discussing before, these are the parameters. Otherwise, the rest of the code will be exactly as it is. But as you can see this time, we don't need to supply the number of images or the number of classes. I think SageMaker should do the same for its inbuilt algorithms also, because this information can be inferred from the input data we are providing, right? All right, so these are the two hyperparameters we are supplying. And then, so the code will be very, very similar to the image classification model using PyTorch framework, right? So first we extract or retrieve the image URI, okay, by supplying the model name and the model version. So the model name is this TensorFlow object detection one SSD. So it's still the SSD model, and the features are extracted using this ResNet 50 that act as a head. Maybe we will have separate video on what are all these different models, what is different about them, how they work, etc. But that might involve quite technical details. Okay. All right. And then we extract the source URI which contain the entry point. So when we do the training, this will be transfer underscore learning.py, right? So this zip file will have that file. And then the initial model artifacts, basically the weights, okay? So if you extract this file, so when you run these two commands, okay, when you run this one, you are simply extracting or finding out this string. Whereas when we run these two commands, we are downloading these two files. Are we downloading? No, we are not downloading, but we are accessing the data from these two paths. Okay. And this one source directory that contains the entry point file. If it's training, that would be transfer underscore learning.py. If it's inference, that would be inference.py. And this contain the original model artifacts. Okay. Then we define the output path. All right, we extract the default hyperparameter by supplying model name and version. And this model, it has a bunch of hyperparameters. And if we want to change any hyperparameter, we can explicitly set the value. Okay. Again, the important ones. Sorry, 1 second. Early stop writing initial accumulation. Train only top layer false. As we are doing transfer learning, should this be true? I'll check that. Train only top layer. I think this should be true, which is the case for image classification. So let me open that file. So classification using this. Now, so this is the image classification we did through transfer learning. So train only top layer true. Okay. So if we want to do transfer learning, I think then by default, this variable seems to be false. So what we need to do is we need to do hyperparameters and then train only top layer. We must set it to true. Okay. Then it will be transfer learning. Otherwise, we are training the model from the beginning. So even the head layer weights get learned from the data we are supplying. Okay. Then this optimizer learning rate. So all these we can leave as it is. Okay. And the number of epochs. So basically we set two hyperparameters. One is this, the number of epochs, and then we are enabling the transfer learning. Sorry, I thought this is by default true, right? Because in most cases we want to do transfer learning. So this should have been true by default. Okay. All right. So I have trained the model with this variable as false. So that means the model will have very, very poor accuracy, right? That's all the difference, but the process is exactly the same, right? And then we get the estimator. Some of these variables, as you know, already are fixed. What changes is this image URI, and for non-inbuilt algorithms, we need to supply the source, and the source along with the source will have the entry point, which is this transfer learning.py, and then the original image artifacts which contain the model weights. Okay, the instance type, the hyperparameter we set explicitly, and then the output path. Okay, so I'm trying to make the video short. We are going it quickly. Now this is important and this is different from the three prior videos. Now, if you look at the train, so here the path contain both the images as well as the annotations. In earlier cases, those two were sitting in different folders, right? But whereas here, both of them are sitting at the same location. Okay, so here we are supplying the bucket prefix and then train. Now this is important, right? This hyphen, not hyphen, sorry, this slash is very important. Okay. All right. So it will read both the train images as well as annotations from the same location. Now, I think this model, it can take only the training data, and by default, it split the data into train and test with 80 to 20 percentage of the data. Now, when I tried to run the model by explicitly providing the validation data, I think I got some error. It could not understand what this variable means. So we only supply the training data. Now the model automatically dividing it into train and test, and during the training process, it's checking the performance on the test data. The model has split. Okay. All right. Then the job name, and then simply do the fit, the standard method. Okay. All right. Again, all these things are standard. We have seen 3 times by now. Somewhere in the logs it says I am dividing the data into train and test with 20% keeping for testing. Yeah, it will be somewhere in these logs. I saw it. Okay. All right. So the model gets trained. Okay, so this is explicitly saying I have uploaded the model artifacts back to S3 location we have provided. And then the inference, as we were discussing, for these models using other frameworks, the train instance URI and the infer instance URI or the Docker image will be different, right? So that's why here we are explicitly retrieving the Docker image for doing the inference. Again, the model and model versions will be the same, but whether we are doing the training or inference is different, and we have different Dockers for that. Okay. And similarly, we are extracting the entry point script. Okay. So this would be inference.py. It takes exactly the same variables. I mean, the model ID and the version. Okay, only the scope will be different. Now again, can you guess why we are not extracting the model URI? The reason is we just have trained the model. So we already have the model with the weights fine-tuned for our data, right? So when we deploy the model, the estimator, it already know where our model artifacts are. Okay, so it uses these two pieces of information and the model artifacts sitting on our own S3 to deploy the model. Okay, so again, we specify this entry point as well as the source directory. The source directory actually contains this script. Okay, so here we are just saying here is the folder, but within that folder, the file name is inference.py. Okay. All right, then the inference instance type and the count, that's a standard thing. And we are providing the names. It is doing the standard three things, creating the model, config, and actual endpoint. Now the inference is exactly the same as we discussed, whether it is classification or object detection, or maybe we will look at other use cases as well. There are a few different variants for the segmentation, a few tasks similar to that. We will cover those as well. All right, so here we have the output format. Again, we will discuss this in more detail later, because we are going to analyze this data, compare against the ground truth to find out the model accuracy, etc. But it seems like it has these two values, those normalized boxes and then the scores. So these are all the detections, meaning we need 4 values. Now this is rubbish really. So it's simply saying 0 to 1, 0 to 1. So the full image, that's again because it's not transfer learning and we trained for only 5 epochs. So the model hasn't learned anything. Okay, it's rubbish. Okay, so here we have the classes. Okay, so we have 3 values, right? The boxes, the classes. So it's saying it's this class 3, and then probability for each class. Okay, now as we discussed, object detection model, they return a number of detections. Okay, 90% of them with very low confidence score. Now when getting the response, here itself we can restrict how many detections we want. So here we are saying I want the number of predictions to be only 5. There is probably an option to say, okay, I want predictions with a score above a certain threshold. Okay, so there may be another method, other way to check or to restrict the number of detections returned. Okay, again, don't forget to delete the endpoint. Okay, so a quick summary of the 4 videos. We have trained image classification, object detection models using inbuilt algorithms and external frameworks. So in the next series of videos, we are going to work on how to prepare this data, right? How to prepare the data, how to create the annotations, etc. So that's the first set of videos. And in the follow-up videos, we will work on how to assess the model performance. So we are going to take the predictions as well as the ground truth, and we will compare it to find out the model performance. We will measure it using various metrics like classification, accuracy, the confusion matrix, the precision, recall, true positive rate, false positive rates, etc., etc. And also for object detection models, we can have different thresholds for different classes. For example, let's say identifying dogs is easy. So the model might detect dogs with very high accuracy. So we might say, hey, if my confidence score is only above 80% or 0.8, then only I take that as a detection, right? If detecting cats is difficult, we might choose a low threshold value, right? So we are going to discuss all that. So we are going to, for various thresholds, we will find out the precision, recall, and how to balance the precision and recall, how to choose different thresholds for different objects, etc. So we will cover all that. Okay, so we have covered only the training model. We have skipped the data preparation as well as the post processing or the model assessment, which is the most important step. That's all for today. Thank you very much. Hello friends. In the last few videos, we have looked at how to train image classification and object detection models using Sagemaker's inbuilt algorithms as well as Jumpstart algorithms using TensorFlow and PyTorch. But we have skipped the data preparation part, right? We did not look into how we prepare the images and the annotations, right? So today, in the next few videos, we are going to look at the data preparation for image classification and object detection models. Okay. Now, generally, we use some tool to annotate the images first, and then we get the annotations. And as we discussed, different models takes the ground truth in different formats. Okay. Then we convert the annotations created by the tool to those which can understand by different models. Okay, so there is an intermediate step. Now I have uploaded another video series using a web-based UI tool called Make Sense. So please watch those videos first. We are going to use the output from the Make Sense to create input for Sagemaker inbuilt models and also the Jumpstart models. Okay. All right. So let's start with the image classification models and the LST format, right? So we have trained the model using these 4 folders: train images, train annotations, and also validation images and validation annotations. Now, the images contain simply the images, but the annotations, they contain this LST format file, right? So today we will see how to prepare this LST format and how to prepare the data into train and test, etc. Okay. So I will show you what we are going to create. Okay. So this is the LST format, right? So for each image, we have one label and we have converted the label to some label ID integer starting from 0, right? So the first column is just the serial number and the second column, the label ID, and finally we have the image name, right? So that's for the train. So for example, in this case, we have some 70 images, right? And then we have the validation LST file, the index starting from 71. Again, we have a bunch of images and also the 3 labels. Okay. So that's what we are going to create today, starting with this file. So here we have a folder that's where we start with. So right, so let's say we want to train image classification model, so we collected a bunch of images, all right, and then we used Make Sense to label these images. So this is the output from Make Sense. Okay, so it's a 2-column file. We have the image name or the file name, and then we have the object or the class name. Okay, we have this class name, one for image. We are going to use this file as an input to create this file, right? And also we are going to split the images in this folder to train and test, and then we copy the train images to train, validation images to validation, and we will create 2 LST files and we copy them into train annotations and validation annotations. We will create one more file called this labels map, right? So as you know, for machine learning models, they only work with the numbers, right? So after training the model, we get back the class IDs. So in order to map these class IDs to the classes, we will create this simple JSON file where we have the class ID to class labels mapping. Okay, so we are going to create this file as well. All right. So let's jump into the code. Okay, so let me go to full screen. All right, so quickly again, we are starting just with this folder, right? A bunch of images uh, uh, and this file. Okay. All right. Okay. So we have looked at all these libraries before. So here we have a new library called Shuttle. Using this, we can copy or move the files from one location to other location using Python. Okay. Now here we have created 4 directories: train images and annotations, validation images and annotations. Okay. And then first we read the annotations file created using make sense. Okay. So as we discussed, this file don't have the header. So here we are creating the column names. So the first one is image and the second one is this class. Okay. So we are going to use this file to create the LST file. All right. So let's say, let's define our train and validation split. Let's say we want to create 70% of the data for training and the rest 30% for validation. Okay. So here, because this is image classification, each row is unique. For object detection, we can have multiple rows for the same image because it can contain multiple objects, right? So here we are simply taking the number of unique images, or we can even take the length of the data frame. That would give us the total number of images we have annotated, right? And then we are just from the total images, we are just finding what is 70% of it and what is the remaining images. So for this one, I have annotated 100 images. So that means we are going to have 70 images for training and the rest 30 images for validation. All right. Now, the makes sense. It has created the label in the form of this list, right? Now we want just the label. We don't want this bracket, a square bracket at the beginning and at the end, right? So here all I'm doing is I'm taking this class column and just excluding the first and the last character. Okay, we are simply excluding the square brackets here, right? And we write that back to the class column. Okay, so here we have just the class as it is. And then first we want to create the mapping file, right? So the labels we have, the apple, orange and banana. Now it is up to us how we want to index them. For example, I mean, if we might, if you, so here I'm choosing 0 for apple, 1 for orange and 2 for banana, right? So this order does not matter as long as once you choose the order, you should use the same order throughout your project. Okay. All right. So just using some key value pairs, I'm just accessing, creating an empty a dictionary. So the enumerate with the labels. So what it does is it returns the label one at a time, and also the enumerate return the index. Okay. So we have created this key value pairs and we have simply written this dictionary, labels map dictionary to the to this file location, right? So basically we just created this file, labels map dictionary, right? We have created that file. All right. And then so using this mapping file, now we map the classes to the classes ID. Okay, so the banana gets mapped to 2, orange to 1, and apple gets mapped to 0. We can't see here, but it's there. So here we are looking at the top 5 rows of the data frame. All right. And then we want to make sure before we split the data to train and test, we want to make sure we have randomized or we shuffle the data well, right? So for example, for some reason, maybe all the images at the beginning might be orange, right? So when we split the data to train and validation, we don't want all the images tagged to orange. only to be in the training data, right? So we want to shuffle this data frame so that when we split, we have roughly equal proportion of all the classes in both train as well as validation. Okay. So here what I'm doing is simply using this sample function, which sample the rows from the data frame. We are without replacing. Okay, that's important, without replacing. And we are saying the fraction is equal to 1. So what it means is we are going to get all the rows from this data frame one at a time and add them back to the data frame without resampling, right? Without replacing. Okay, so this way we still get the same data frame, but the rows, those are shuffled. Okay, all right. And then now, as we saw for LST format, we need to have this index starting from 1 in column 1, right? So here I'm simply using the data frame index column, which start from 0 and added 1, so that we created this new column called index. Okay, so for each image, now we have an index, a unique index, right? All right. Then it's very simple. So we want to create this LST file, which should have 3 columns. So the first column should be index, the second column should be class ID, and the third column should be the image name. Okay. So I'll again show you the format. Yeah, sorry. What is it? Yeah, so this is the file we are going to create, right? So first in column, we have this index, and second, we have the class ID, and the third one, the actual image. Okay, so this data frame has 4 columns. So we have simply created this selection columns with index first, class ID second, and image third. Okay, and then we are selecting these 3 columns from the data frame, and then using the head, we are selecting n train number of images, right? So here we found we want to use 70 images out of 100 images, 70 for training, 30 for validation. All right, so what we are doing is using the head and in train, we are selecting the first 70 rows from the data frame, and then we are writing to a file. Okay, so we are writing to this file called train annotations and train LST. So even though we are using this CSV, the extension don't have to be CSV. Okay, the important thing here is the columns of this file should separated by /t rather than a comma, as is the case for a CSV files, right? CSV file name means comma separated values, right? But here we are creating this LST file and the separation should be /t. And then we don't want index. So whenever we use pandas to write to a CSV file, by default, it create this index which start from 0. Okay, it write that index also to the file. We don't want that index. And then we also don't want the headers. So as we saw here, this file, it does not have any headers. Okay, so the training model, it expect the actual data from row 1 itself. So that's what we did. So we have created that file. Now here we are looking at the top 5 rows of the file. So let me look at it. All right. So this is what we created, right? So the index, the class ID, and the image name. All right. And then, so here we are doing the same thing, but this time instead of head, we are using the tail that would select the rows from the bottom, and we want the bottom 30 or in validation number of rows, right? So that would select those 30 rows, in this case 30% of the data, because we have 100 images, we have 30 images for the validation. Okay, so we have created the validation LST file. All right, and then we need to copy the data. Okay, so here we have created these 4 folders. We have created and copied the files to the respective folders. Now we need to copy the train images to the train file and annotation images to the annotation folder, right? So that's what we are going to do next. Now here what we are doing is, so from the LST file, we are reading the LST file here, right, as a train or data frame. Now we already know which images are in this file, so we could use this one to figure out what images should go to train folder, and then this one to figure out what images should go to validation folder. But here I'm just to make sure we want to move only the files which are in the LST files. We are reading the LST file again. Okay, so we are reading the train LST file using again pandas CSV, but by default it expects comma separated value. So we need to explicitly state, hey, these are separated by /t tab, and then this file don't have a header. Okay, so these two are important. Otherwise the first row is taken as the header by default. Okay, so we read this file. Now from this file, we know the second column because it does not have header. So we are choosing the second column. So the second column contains the image names, right? So the second column that contains the image names. So here what we are doing is we are selecting all the image names as a list, and then we are going over the images one by one, and then we are copying the images from our source folder to the target folder. So as we saw here, this is our source folder, right, where we have all the 100 images, and then the labels file created using makes sense. Now we want to copy the train images from this folder to the target train images folder, and similarly validation images to the validation images folder. Okay, that's what we are trying to do. So for each image, copy from this location, which is this all images and ground truth, to the train images. Okay, so we are copying the train images, and then we are doing the same thing for the validation images. So here we are reading the validation LST file and going over all the validation images and copying the validation images from this all images GT file folder to the validation images folder. Okay, all right. That's it for the video. Thank you very much. See you in the next video. In this video, we will learn preparing the LST format ground truth file for image classification using the subfolder structure. Okay, so here we have our images folder. We have already separated the images into different classes using these 3 subfolders, right? Here we have these 3 subclasses. Now, as we saw, in order to train the image classification model, we need to prepare the data in this format. We need to have train images in the train one folder, and then we have the train annotations in the form of this LST file, and similarly for the validation images and annotations. Now this LST file, it takes a particular format, right? For example, here is the format. It's a 3-column format. First column have the image ID starting with index 1, and then we have the class ID. So we map the class name to class IDs, and then we have the actual image. So here we have only this, right? So we have created a folder and subfolders, one for each class, and then we already have within each folder we have the images belonging only to that class, right? Now, so in this case, we don't need any tool like make sense to create the annotations, right? Because it is already clear from the way the images have been organized. Okay, but we still need to create the LST format file because that's what expected by the Sagemaker. Okay, so what we are going to do is we are going to create these 4 folders. We are going to copy the train data to train images, and then going to create the LST file for train, similarly for the validation, and finally we are going to create this mapping file between the class IDs to class names, or the label IDs to labels. Okay, all right, so let's start from here. Okay, from subfolders. Okay, so here all the we already know all these libraries. The shuttle, as we discussed in the previous video, we are using it to copy the images from our source directory to different target directories like train images and validation images. So first we create these 4 folders. So we are creating these 4 folders, and then we define 2 empty lists. One is for images and the other one for classes. So what we are going to do is we are going to read the content of this folder to find out all the images within these folders and the corresponding classes. So the class name coming from the folder name. Okay. All right. So using this OS walk, we give this root path, right? So our root path is all images. So our root path is all images. Then we will be reading all the content from this all folders. Okay. So it will return these 3 things. One, the path, the subdirectory, and then the file names. Okay. And then we are going over the files one by one. Okay. So this will return 3 lists. Sorry. So it will return a list, and we are accessing the list elements one by one. And then for each file, because I'm working in Mac, there is this file created automatically, this ds_store. So if it's this file, we just want to ignore, right? So we are just ignoring. Otherwise, we are taking the file and adding it to images. Okay. So these ones we are reading as files. Okay. And then the path will be this whole thing. So all images / Apple, all that thing will come as the path. Okay. So from the path, we are splitting it by the slash. Okay. So that will return a list, and our class is this last element, right? This last element. So we are accessing that last element. Okay. And we are adding that to classes. So after running this code, we will have this images list as well as the classes list. So the images list looks like this. Okay, here we are printing only the first 5 elements. Okay, so this OS walk, it first reading this folder called Apple, and it reading these images one by one, are the files. So here we have all those file names, and then from the path we split the last element name, which is the class name, right? So for the first 5 images, it's apples, because it's reading the apples folder first. Okay, so that's what we have created. So using that subfolder structure, we have computed, or we found out all the images in our main folder, and also for each image the class name using the subfolder name. Okay, all right. And then here we are creating this folder, a data frame with 2 columns, the images and the classes. Okay, the images and classes. Now, this data frame is exactly similar to what we would have gotten from make sense if we used make sense to annotate the images, right? Except these elements are not in the form of list, so those are directly as a string, right? So from this point, it is straightforward. It is we are going to uh, we are going to use the same code which we used in the previous video to create the LST files. Okay, so essentially what we are doing is, from the total number of images, we are we are finding out 70% of the images for training and 30% of the images for the validation. Okay, and then uh, we are creating a mapping between the labels to the label ID, and then we are saving that to the labels map JSON file. Okay, so this part of the code I am going over it very quickly because we have covered this in very detail in the previous video. Okay, and then using the class and the labels map, we are creating the class ID. Okay, so we have created the class ID column, and then to make sure that the images belonging to one class, not all of them go to train or the validation, here we are doing the shuffling. So using the sampling function, we are sampling the rows from the data frame, and with the fraction is equal to 1 means we want to get back all the rows, but in a random or different order, right? So we have shuffled the data frame, and then because the LST file expects an index column at the beginning, so here we have used the pandas inbuilt index column, which start from 0 and simply added 1 to it to create the index column. Okay, and now we are going to create the LST file using this data frame. Now we know the LST file format. It's the serial number, the class ID, and the image name, right? So we want to select these three columns, the index, class ID, and the image name. So from the data frame, we are selecting only those three columns, and also using this head, we are selecting the first n number of images, which is n train images, right? We are writing it to this train LST file, and as we discussed, the CSV file by default, it separates the fields by comma, but LST files, it should be separated by /t or tab. So we are explicitly saying, hey, when you are writing the CSV or LST file, use tab for separating the fields, right? And also by default, pandas, it write the index as well as the column headers, which we don't want in the LST file. Okay, so that's why we explicitly stated, hey, don't write those. And then here we are looking at the top 5 rows of this file, train LST file, and it is in the format we expected. Okay, and similarly the validation file. And finally, what are we doing here? Right, so here we have all the images in these subfolders, right? Now just creating a temporary folder, this all images temporary folder, and copying the images from those subfolders to this one folder called this all images temporary folder. Okay, we are going to delete this folder. The reason we are doing that is, once we have all the images from these folders in a single folder, using the LST files, we can find out which images should go to train and test, and we can easily move them, right? So here we have read the LST file, and then from the second column, we find out which images should go to training folder, and we are going over the images one by one. And from this all images temp folder, which contain all the 100 images from those three classes, Now we are copying the train images to the train folder, right? We are doing the similar thing for the validation images, okay? And finally, we are deleting this temporary folder we have created, okay? All images temp, okay? So again, just to summarize, we start with this folder, all images, which has these three subdirectories. And then we have created these three folders. We have created the annotations in LST format. We have copied the corresponding images to train and validation. And we also created this labels mapping file. Okay. Now we can use that as an input. We can upload the data to S3 and we can train an image classification model using Sagemaker's inbuilt algorithm. Okay. That's it for today. Thank you. In this video, we are going to see how to prepare the training data for multi-label classification. Okay. So in multi-label classification, each image can have multiple labels. Okay. All right. So this is what we start with. So we have a bunch of images and then we also have the labels file. Now, generally we use a third-party tool to annotate the images. Okay, so we have used this tool called Make Sense to annotate all these images. And I have a separate video series on Make Sense on annotating images for image classification, multi-label classification, as well as object detection. So I provide the link below. Please watch those videos if you don't know how to create the annotations. Okay, so this is the output from the Make Sense. Okay, so for each image, in the second column, we have the annotations. Okay, now so here each image can contain a single or multiple annotations. Okay, for example, the first image, it has both labels, banana and apple, whereas the second image has only apple, right? So whereas this image, it has all three labels, banana, orange and apple. Okay, so we are going to use this file to create the ground truth in LST format, which will look like this train annotations. Okay, all right, this is how it's going to look like. So similar to image classification, the first column is let's say ID, and then the last column is the image name. Now for image classification, we would have only one column indicating the class or the label ID, right? So if you have 5 labels, that second column can take values from 0 to 4. That's when we have a single label for each image. But now that we have multiple labels for each image, we need multiple columns to capture that information, right? So that's what we have here. So this second column, it represents if this image has that label or not. So 0 means this image don't have this label, right? And also this label. So this image contain only this label. Now, from this LST format, we wouldn't know what the label name is, right? Because all these LST files, they'll contain only information about label IDs. We typically will create another file called this mapping file so that we can map the label IDs to the labels, right? For example, label 0 is apple. So what this means is 2 is banana. So that means this image contain only a banana, right? Whereas this image, it has all three, apple, orange and banana, like that, right? So we are going to use this this output from Make Sense to create this LST file. Okay, and also will do the train test, the usual thing, right? So this is our input, all the images as well as the output from make sense, right? And we are going to take this as an input and create these 4 folders with the annotations files as well as this mapping file. Okay. All right. So here we are first preparing these 4 folders, multi-label. Yeah. So we are creating these 4 folders and then reading the data or the output from make sense. Okay. So this is what we have. So it's a 2-column file. We have the image name in the first column, and the second one, it looks like a list, and it will have the label names. Okay. Now this output from make sense, it does not have the column headers. So here we are creating the column headers. Then we are simply splitting or finding out how many images should be used for training, how many for validation. Okay. All right. And then, so from this one, we first want to get rid of the square brackets, right? Square brackets at the beginning and at the list. Now there are multiple ways to achieve this, but here I'm showing you just one way. Okay. So from this one, we have removed the square labels, right? So all we did is we use the apply function from pandas. So we took the row or the cell value one by one, and we have selected from index 1. So this is a string, right? So index 0 is the square bracket. So we have selected from index 1, meaning we have excluded the starting square bracket, and with -1, that's from the right side, we have excluded the right square bracket. Okay. All right. So now we have this one. Now we want to create the mapping file. Again, it is up to us how we want to create mapping, whether we want to create map apple to 0 or apple to 2. It is just up to us. But once you fix, you should use the same throughout the project. Okay. So these are the labels we have. We have created this label mapping dictionary and written it to the this location. Okay. So we have just created this labels map file. All right. And then now, so we have this class, we have the labels map. We want to use these 2 pieces of information to create a list like this. Okay. So for example, here, this list, it contains 3 elements to indicate if this image contain each of those labels or not, right? For example, it contains this banana and apple. Okay. Now here, so banana and apple. So apple is 0, banana is 2. So it contains the first and third label. It does not contain the label in the middle, right? So that's what the 0 indicating. So we want to make use of this class information and then the labels map information to derive this column. Okay, that's what we are going to do. So here I have defined this function, and then for each row or each cell of this value, for each of these values, we are applying that function. Okay. Now the way we are doing, first we split whatever we have here using the comma. So for example, this one, it's split into banana apple as a list. Okay. And then we are simply checking which of these labels exist in this list we found. Okay. If it exists, we are adding 1. If it does not exist, we are adding 0. Okay. So we are creating this new list with 3 elements, and the values can either be 0 or 1. 1 if the label exist here, 0 if the label don't exist. Okay, that's what we are doing with that function by checking if the labels exist or not. Okay, now once we create it, it's pretty straightforward, right? Then we can apply this pandas series uh, to uh, to split this column into as many columns as the number of elements in this list. Okay, so this column we have split into 3 columns, and the label or the column names should be the labels. Okay, because we have used the labels to derive this column, right? So yeah, so again, just going back here, apple and banana 0 1. So we have apple and banana, we don't have orange for this image. Okay, now it's easy. So we are just shuffling the data or shuffling the rows from the data frame uh, to make sure we have even distribution for the train and validation for the classes. And then we are creating the index here using a pandas inbuilt index column. Okay, we have the index. And then, so from the LST file, we know first we should have the ID or the index, and then we will have the number of columns equal to the number of labels, and finally we have the image name, right? So here what we are doing is we are creating this new list with these elements. So the index, and in the middle the labels, and finally the image name. Okay, so from this data frame which has these additional or multiple columns, we are selecting the columns we are interested in, those columns, and then using the head function of pandas and also the number of train images we have selected. So basically we have selected the first n-train number of images from this data frame with these columns. Okay, and then we are writing it to a LST file. Again, these values should be separated by tab, and there should be no index, and also there should not be any header. Now this index is shown by this UI editor, but we don't have the index contained within this file. Okay, all right. We have written this file train.lst file in this train annotations folder, and then if you look at the top 5 rows data, right? Okay, so this is what we have, exactly what we are expecting. Okay, and similarly we do the same thing for the validation images, right? And finally we want to copy the folders from this all images folder where we have all the images, the train images to train, validation images to validation. So here what we are doing is we have read the train LST file and we know the last column. So from this train data frame, this will return us the columns we have, and -1 that will give us the last column name, or okay, the last column. So we have selected all the image names as a list, and then we are going the images one by one, and then using this shuttle function from Python to copy the images. Okay, so we are copying from this source location, which is this all images ground truth, to train images. Okay, because these are train images. And similarly we are reading the validation LST file, we are finding out the images from the last column, and then going over the images, copying the images from all images GT file to the validation images. So here GT means ground truth. So this all images GT folder contain all the images along with their ground truth. Okay, all right. So starting with this images and the output from make sense. We have created these folders, prepare the data for multi-label classification using Sagemaker. That's all for today. Thank you very much. Hello friends. Today we will see how to prepare the data to train object detection model using Sagemaker's inbuilt algorithm. Now, preparing the data for object detection is much more involved compared to the classification, because we have these objects and the bounding box coordinates, also the image dimensions, etc. Right? For classification, it's simply an image and a tag. Even for multi-label classification, we can have multiple labels, but that's about it. Whereas for object detection, we need much more information like the image dimensions, the bounding boxes and their coordinates, etc. Okay. So to begin with, we have all the images here, and we generally use an image annotation tool to create the labels. Okay. So in this case, I have used Make Sense. It's a free and open source browser-based tool for annotating the images. Okay, so I have used that tool and I have already annotated the images. Okay, now I have a separate video series using Make Sense. Please watch those videos if you don't know how to create the ground truth. Okay, so we take this as an input and we want to create the annotations or the ground truth in this format. So unlike image classification, for object detection, some models expect one annotation or one JSON file per image, or some other models, all this information can be within one file. Okay, but for the Sagemaker's inbuilt SSD model, it expect one JSON file per each image. Okay, now the format of JSON file, it looks like this. Let's look on VS Code because we can format it. Okay, so this is how the JSON file should look like. Okay, now it contains 4 sections. So the first one is this file, which is simply the image name. Okay, and the second one, the image size. This is a list, but with only one element, and that element is a dictionary with 3 values or 3 key pairs. Okay, so the image width, the image height, and the depth. So for color images, this value is 3, always 3. Okay, so that's image size. And then we have the annotations or the bounding boxes information. Now this is again a list. The number of elements depends on how many objects we have. For example, in this case, this image, it has 2 objects. Okay, so the first object is this one and the second object is this one. Now each object we identify with 4 coordinates, right? Using the top left coordinate and then the bounding box width and height. Okay, now different algorithms or models takes this exact information in different format. For example, in addition to this top left coordinate, we can have bottom right coordinate, right? Instead of the width and height, we can have the bottom right coordinate. So those 4 values also are enough to infer the box coordinates, right? Or we can have the top left coordinate along with the width and height of the bounding box. Okay, so and for each box we have the class ID. Okay, because an image can contain multiple objects and these multiple objects belonging to different classes. Okay, and this is for the second object. Again, we have the 4 coordinates and also the class ID. And then finally the 4th section, which is this categories. Okay, so it's supposed to it contains the mapping between the class ID to the class name. Okay, now what I noticed is this categories information, it can contain all the labels and their IDs. It don't need to contain only the categories or the objects this image has, right? For example, in this project we have three labels, right? For example, we can have uh, like this. For example, this one, which is this orange. Okay, so even though this image does not contain an orange, the categories list can contain all the categories of this project. Okay, that's what I noticed when I trained the model. So what this means is probably this categories information is not really used during the training, or maybe it simply ignored this additional information we have for that image. Okay. All right. So let's go back to the code. Okay. So quickly, we are going to use this file, which is the output from Make Sense, to create a number of files, one for each image, in the form of this JSON files. Okay. So all our images and the labels file are again in this all images and ground truth folder. We are going to create these 4 folders, and we are going to create all these JSON files. Okay, and then we are also going to create this mapping file. Okay, so let's get into the code. Now here we are creating the 4 folders, and then reading the output or the objects from the Make Sense. Okay, now this file contains 8 columns. Now unlike image classification annotations, for object detections, the Make Sense output contains the column headers. Okay, so we don't need to provide the column headers. So it has okay, let's start with this image. Okay, so we have the image name and then the image width and height. Okay, and then finally for each image we will have the object the label or the object name, which is one of these 3 in this project, and then we have the box coordinates in the form of this box x and y. So this is referring to top left coordinate. So the x is left, okay, y is top, and then the box width and height. All right, so here we have figured out how many images we want to use for training and validation, and here we have created this mapping file to map the classes to the class IDs. Okay, now so we are going to use this label name column to find out or to map it to class ID. Okay, so using this mapping, so here we have simply created this additional column where we have the mapping between the class name to the class ID. And then as we saw from this JSON file, it expects these keywords like left, top, width, height, class ID, etc. Right? So for convenience, what we are doing here is we are converting these 4 names, this bounding box x, bounding box y, and then this bounding box width and height, to simply left, top, width and height. Okay, so that we can create this file a bit more easily. All right, so we have simply renamed the columns. So using the pandas rename function, and we want to rename the columns because we need to explicitly state this is columns, otherwise it expect it to be index or rows. Okay, so this is the columns map. Okay, so all we did is we simply transform these 4 column names to these 4 column names. Okay, all right, and then so we want to first let's create this category section, which is the easy part, right? With this category section, as we discussed, maybe I'll show on the here. So as we discussed, this is generic and it can contain all the categories. Okay, so let's create that first. Okay, so using this labels map file, we simply created this categories just in the form of the Sagemaker expectation, right? The ground truth format. So we have the class ID and the name. That's for label 1, and then we have second element and we have the third element. Okay, so we have created this categories part. So out of these 4 sections, we have created this generic one categories. Okay, now as I said, it's a bit involved compared to classification, but again it's not difficult. Okay, so first let's access all the images. Okay, so from the data frame, using unique, we are getting all the image names in the form of a list. Now the reason we are using unique is because unlike classification, the number of rows can be more than the number of images, right? For example, even though we have only 100 images, the number of objects is 161. So the number of rows is also 161. For example, okay, this image, it contained 2 objects. Okay, whereas this image, it contained these 3 objects. Okay, so that's the reason we are using unique here. Okay, so we have collected all the image names. Now we are going to create one JSON file per image, right? Not per object. So we are looping over all the images. Okay. Now this data frame, it contains the data about all the images. But now we are creating this temporary data frame called image data frame. Okay. By simply uh, uh, filtering out, right? By simply, so we are using this image name from the original data frame, and if this image name is equal to our selection image, then we are subsetting or filtering this data frame. Okay, so now this data frame contain only rows related to this particular image. All right. Now let's create the second section, right? Now let's create this image section of the ground truth. Okay, so it contains 3 elements: the image width, height, and the depth. So let's get back here. Now we are creating the image section. Okay, so as we discussed, it's a list with only one element, and it has these 3 values, right? It's again that one element is a dictionary, and this dictionary contain the width of the image, height of the image, and the depth. Now the width of the image, so here we have this image data frame. So from this image data frame, we have the image width. So we have the image width. Now if this image contain multiple objects, what we get here is multiple rows, right? But the image width and height are not going to change for the object. These are sort of global, right? These are image properties, not object properties. Okay, so that's why we are simply saying, okay, my first row, so get me the value from the first row, because for the second row, if it contain 2 objects, the values still be the same, right? Because these are image properties. Now this int, just to make sure, sometimes when we read data from files, it's read as floats, etc. So this is just a safety. Okay, so here we have collected the image level properties, which are this image size. Okay, so the second one is also done. So earlier we have defined the categories, and then for each image, now we have defined the image. Now the main part, this annotations part. Okay, so let's go here. Now we are choosing the annotations, right? Now these annotations can be multiple for each image, right? So here what we are doing is from this image data frame, we are selecting these 5 columns. Okay, so the 4 related to the object dimensions, and the first one the object ID or the class ID, right? So here we are selecting this column, the class ID, and then the 4 columns related to that object. Okay, now this can contain multiple rows, right? Because if an image can contain multiple objects, but we have a convenient uh, pandas functionality, which is this to_dict. Okay, so we can convert a data frame to dict with orient as records. So what this does is it automatically convert the data frame to this format, right? So the exact format we want it. Okay, so we have the annotations as well. Okay, now finally, so these annotations again are just reiterating, this can be multiple records. Okay, so this will be a list with as many dictionaries as the number of objects. All right, finally we are preparing this ground truth dictionary with the 4 elements. So the first one is the file, the image size which we computed for image, and then the annotations part, and finally the categories which we made it generic, right? So this categories, it's going to contain all the categories whether this particular image contain that category or not. And as I said, object detection algorithm, it's fine with it. Okay, I don't know if that is intentional or not from Sagemaker, but the generic or the full information is also working. All right, so we have prepared the content of this file. Now we need to write that file. Okay, now in this part, what we are doing is we want to divide the data into train and test, right? We want 70% of the data to go as train and the rest 30% should go to validation. So what we are doing here is we are uh, generating a random number using that random library from Python. Of course, all these libraries are from Python. So this value will be between 0 to 1, and all the values are uniformly sampled between 0 to 1. Okay, so what we are doing is, if this value is below 7, now I want to go that image to the training part. If that value is above 0.7 or equal to or above 0.7, so this is this else part, we want that image to go into the validation part. Okay, all right, so let's say the random number we generated happened to be below 0.7. So that means we need to copy the image to the train images folder, right? So from this source directory, all images and ground truth, which is this one, where we have all the images and all the output from Make Sense. So we move the file to the train images, or we simply copy the image, right? And then corresponding to that image, we need to create the annotation file or the JSON file, right? So train images, okay, this file, train annotation, train annotation, yeah. So this JSON file. So what we are doing is we have created a JSON name. So this file should go to train annotations, and then this file name should be the same as the image name, except that it should have the .json extension. Okay, so what we did is we took the image name, we split the image name using dot. So for example, if the image name is so and so where is it? So and so dot JPG or PNG, etc. So we split it using this dot. So that gets split into two elements. So the first element contains the image name and the second element contains the extension. Okay. So we took the first element, so which means we took the image name without extension. And here we are adding the JSON extension and then writing to the file. So this file, it will be going to this train annotations with name same as the image but with extension JSON. Okay, so we have written the file to the annotations folder. Okay, same thing we are doing here, but if the random seed is below 0.7, we are doing it for the validations folders, the images and the annotations. Okay, here I'm just showing you one example of this ground truth dictionaries we have created here. So this one, right? So the ground truth dictionary we have created, that's for the last image. Okay, so it contains 4 sections as we discussed. First, the file name, and the second one, the image size attributes, the width, height and depth, and the next one, the annotations. This is again a list and each element is a dictionary, and the number of elements is equal to the number of objects the image has. So in this case, this one happened to have 2 objects, and each object will have these 5 sets of information. The first one is the ID, and the remaining 4 are the coordinates to identify the bounding box. Okay, and finally we have the categories, which is, as we have discussed, can be generic. So it contains all the categories. Okay, so that's the 4th element. All right. Again, in summary, we have started with this all images and ground truth folder and a labels file created using make sense, which look like this. Okay, which sorry, is it this one? Yeah, that's the one. So which look like this. So for each image, we'll have the labels and the bounding box coordinates. Okay, and also the image dimensions. So we took that as an input, and then we have created these 4 folders and a mapping file. Copy the images to the corresponding folders, and then for each image we have created one JSON file, and the JSON file in this format we just discussed. Okay, so using this data prepared, now we can train an object detection model using Sagemaker's inbuilt algorithm. Okay, now as you know, there are hundreds of different object detection models. Now different models take the data or the ground truth in different format. So they still contain the same information, but in maybe slightly different format, right? So in the next video, we will see how to prepare the data to train a TensorFlow model using the Jumpstart. Okay, so the format will be slightly different. We will do that in the next video. Thank you very much. In this video, we will learn how to prepare the data for training object detection model using Sagemaker's Jumpstart TensorFlow. Okay, so the Jumpstart TensorFlow model expect the data format slightly differently as compared to the image classification and object detection models we saw in the previous videos. Okay, for example, the Sagemaker's inbuilt SSD algorithm, it expects these 4 folders, right? So the folder names can be anything, but it expects all the training data in one folder, the training images, and then the training annotations. It expects one JSON file per image, in a separate folder, and similarly for validation images and annotations, right? So these 4 folders. Now the TensorFlow Jumpstart model, it expects the data differently. So it's like this. So all the training images and data in one folder like this. Now within this root folder, all the images should be this images folder, and then all the images should be in a single file called this annotations file. Okay, not one image, one JSON per image like inbuilt uh, uh, algorithm. Okay, and similarly all the validation images in this images folder, and also all the annotations in this single annotations file. Okay, now let's look at this format first. Let's see this in Visual Studio. Okay, so the annotations file, it contain all the images data, and it contain mainly 2 sections. So the first section is this images. Okay, it's a list again, and each element is a dictionary containing information related to each image. Okay, so for example, this one, the first image, here we have the image name, the height and width, and ID. Okay, and this information, it's for the second image, the name, height and width, and ID. Okay, so the first half section of this file contains this image information. Okay, so that's it. Okay, so for all the images, their names, their sizes, and for each image there is an ID. And then the second section of this file contains the annotations. Okay, now the way the first section and second section are going to be mapped is using this ID. Okay, so that's why we need this image ID. So even though it's called ID here, it's called image ID here. Okay, so corresponding to each image here, we can have multiple rows, obviously, if the image has multiple objects. Okay, so this one is used for mapping image ID. And then finally, we have the bounding box. It's a simple list with these 4 elements. So unlike SSD model, we don't have a dictionary containing these 4 elements as left, top, width, and height. Okay, so it's simply a list with all the 4 values. And then finally, it contains the category ID. Okay. All right. So we are going to prepare this data for the train and validation using the output from make sense, which is this. Okay, we have discussed the format of this file in the previous video, but again very quickly. So we have the image name in the last 3 columns. This is the image name, and then the image width and height. Okay, so the image width and height, and then in the first 5 columns we have the label name and the bounding box coordinates. Okay, the 4 coordinates. All right, let's jump into the code. We have seen all these libraries before. So here we have first created 2 folders. One is called train image and annotation. So the train images and annotation, and within that folder we are going to create another folder called images. Okay, so we have created another folder called images. We did the same for validation data. Okay, and then we are reading the output from make sense. We are already familiar with this format, and then splitting the data to train and test. I mean, here we are just finding out how many images. The actual splitting happens a bit later. We have created the labels file between the classes to the class IDs, and then we use this labels mapping to create the class ID from this label name. Okay, now in the last few videos, I must be using the word label, class, maybe even object interchangeably. That's because again, these different algorithms, they use different nomenclature. Okay, right? So that's why I'm using these words interchangeably. Now here, one important thing we are doing here is, for each image, it is expecting this ID, right? This ID. Okay, so I mean, let me go to the one. So for each image, it's expecting an ID. Now what we did here is, so using this rank function in the dense method, in the dense mode, for each image we are giving a unique ID. Okay, using this image name column, because this is object detection ground truth. As you know, each image can contain multiple objects, meaning multiple rows. For example, this image contain 2 rows or 2 objects, whereas this image contain 3 objects. All 3 objects are 3 rows, right? So for this image, we want to give one ID. For this image, we want to give a different ID, right? So here what we are doing is, by taking this image name, we are creating a rank in dense method. Dense, what it does is, for each group, for example, this is one group, this is 2 group, right? It will assign the same ID. Okay. Now this 6724, that's because when it did the ranking, it organized the data or the unique images in ascending order. So this image, it happened to have the 67th in that row. Okay, but again, the exact ID value doesn't matter as long as we have each image mapped to a unique image ID. Okay. All right. So then here we have got all the images, right? All the 100 images we have in this data set. And then we are sampling n train number of images. Okay. So basically from this list of 100 images, we have found out 70 images which should go to training. Okay. And then there should be a list. You can take it as a list, right? And then we want to subtract the train images from the total images so that we can get the validation images. Now we cannot subtract the list, but Pandas has this, Python has sets. We can subtract sets. Okay. So here we are subtracting the train images from the total images so that we get the validation images. And if we look at the count here, so out of 100 images, 70 are going for train and 30 are going for test. And these split ratio we found here, right? 70%, because we have 100, 70% is 70. All right. And then if we look at the number of objects the train images and validation images going to have, so here what we did is, using this ground truth data frame, we are filtering the images which are in these train images. Okay. So this will give us a new data frame which contain only the images related to train. Similarly, this data frame contain images related to validation. Now, if you look at the length, that would give us the number of objects, right? So the 70 train images, they have 117 objects. The 30 validation images contain 44 objects. Okay. All right. We get to the final part and the most important one. So we are going to create these 2 sections. One is this images section and the second one is annotation section. So let's start with this images section, right? So it is in this format. It's a list and each element is a dictionary. and each dictionary contain the 4 values: the file name, the image height and width, and the ID. Okay, so here we are defining a function. It takes a data frame as input. Now using this data frame, so it first get all the image names, and here we are defining an empty JSON images list. Now we are going over the images one by one, and then for each image, so here we are filtering the data frame to this selected image. Okay, and as we know, each image can contain multiple objects, so this can be more than one row. But because these properties are image level properties, they are not going to be changed based on the object. We are just taking the first row from here. Okay, the first row from here, and then converting it to a dictionary. Okay, so this one contain the image level properties. Okay, for example, it contains the image name, the width, height, the image ID, and of course all other information, all this information for the first object. Because we are not going to use this first object information, we are only interested in this global image level information. This method works, right? Choosing only the first row. All right. So using this dictionary, we are extracting these 4 pieces of information we wanted. First, image name, which should with the key file name. We already knew it from this image. And then we want the height, width, and ID. So height, width, and ID, they are in this dictionary in the form of image height, image width, and image ID, right? So basically coming from these 3 data frames columns: image width, height, and ID. All right. So we have the image level dictionary, and then that's for the first image, right? Then we are looping over all the images, and we are appending the data to the JSON images and returning it. Okay, so when we run this date function with the train data or train data frame, we will get this first section, right, for all the training images. So we'll get this dictionary part, this part. Okay, now we are going to create another function which will return this information for a given data frame as an input. All right, so here we are creating another function for the annotations part. Now the annotations, it should be in this format. So first we should have the image ID, then the bounding box list with 4 elements, and finally the category ID. All right, so this time we are iterating over the objects, right? Or iterating over the rows, right? Whereas here, because this is image level information, we found out all the unique images and we iterate over the images. Whereas here, because this is object level information, we need to go over all the rows of the data frame one by one. So we are iterating over the data frame. Now we are creating this JSON dictionary, the local variable for this particular object. Okay, so the image ID, right? So the image ID, so it's coming from, so when we iterate over rows, it returns 2 values. One is called this index, whether we use it or not, that's going to be an index or the row ID. And then this one is the actual row, right? This row, we are calling it object. So from the object, we get the image ID and then the bounding box. So it's a list with 4 elements, right? It's with these 4 elements. So the object left, top, width, and height. Okay, so those 4 coordinates. And finally, the category ID. So the category ID, again, we are coming from object class ID. Okay, again, so it must be coming from the class ID. Yeah, the class ID. Okay, So we gather the object level information for one object, and then we are looping over all the object or all the rows of the data frame and appending it to this JSON annotations file, right? And then finally we are returning this file. Okay, so these two functions we are going to call with train data frame and also validation data frame. That's what we did here, right? So we split the data into train data frame and the validation data frame. Okay, so in this section we have called the images dictionary function with the train data frame. We collected it into this JSON images, and then we call the annotations function again with the train data. So we got this JSON annotations. Now as our annotations file, it has these two sections, images as well as annotations. We are simply going to combine these two results. So here we are creating a new JSON with train. So it contains this images, which is coming from this JSON images, and then annotations, which is coming from this JSON annotations. Okay. And we just write the file now, right? Finally. So we are opening this file. We are writing it to this location, train images annotations. Okay. So we are writing it to train images annotations. So first we are going to write this file. Now we have created this file, but we haven't copied the images yet, right? So we are going to create this annotations JSON file. So annotations JSON file, we have, so this one. So we have done for the training data, and we are doing exactly the same thing, but this time for these two functions, we are supplying the validation data frame. Okay. And then we have created the annotations file in the validation folder. So the train one, now the validation one. Okay. And finally, we simply need to copy the files or the images, right? So using the shuttle function, we are going over all the images from the train data frame and copying them from the source file, which is this all images GT. Each image, we are copying it to train images annotations and the subfolder images. Okay. So this subfolder. Okay. So we have copied the images, then we have copied the validation images. And here, if we look at the annotations file in the notebook, this is how it looks like. Sorry. So the first section, images section, each element contains these 4 pieces of information. And the second half of the section is about annotations. Yeah, so this is the annotation section. Again, each element contain information about each object, right? So we map it to the image using this image ID, and then the 4 bounding box coordinates, and finally the category ID. Okay. All right. So we use the images from this folder, and then we use the annotations created using this makes sense to prepare this file for the train as well as for the annotations. Now we can use these folders to train an object detection model using Sagemaker's Jumpstart TensorFlow algorithms. That's all for today. Thank you very much.